everyone. Welcome to the CESM tutorial. I am Hui Li. I am a project scientist here. I work in climate variability, Earth system prediction, and tropical cyclone events. And also, I serve as the chair of the organizing committee this year. So I'm very excited to see everyone here, and I hope you will have a very fulfilling week where you can learn as much you can about the CESM model and make a lot of friends and have a lot of fun, and most importantly, become part of the CESM community. So this is the beautiful Mesa Lab. I'm sure you've already seen the beautiful mountain views when you rode the shuttles up. And we also have some very cool exhibitions in the hallway where you can sign up for one of the lunch tours. We have private tours and exclusive tours for the CESM participants, which we'll talk a little bit more later. And then I also want to first of all make a land acknowledgement. We acknowledge that the Mesa Lab and the whole Front Range is located on the traditional territories and ancestral homelands of the Cheyenne, Arapaho, Ute, and many other Native American nations. So here are the two primary points of contact. On the left, it's me. I'm hearing the echo. I hope it's not annoying. And yeah, now on the right is Elizabeth. So you've already received many emails from Elizabeth, and many of you have already got a lot of help from her as well. So the two of us will be here for the whole week to support you whenever you need. So if you have a question, you don't know who to ask, just come to us. So I'm very glad everyone is here. So we have this great goals of the tutorial is to help you gain a fundamental scientific understanding of the core CESM components and the CESM features. We hope after the tutorial you will be able to run and modify the model and use the output in your own research. And we hope you will have the opportunity to network with peers and the CESM scientists here at NCAR CGD. And you can attain an understanding of high performance computing HPC that is needed for CESM model and other Earth system models as well. We also hope you can perceive this tutorial to be an inclusive learning environment, which we will need the help of every one of you to make this happen. So be nice to each other, that's the main gist. So you will find most of the useful resources on this official CESM tutorial website. If you just Google 2025 CESM tutorial, it will first take you to this site. So you will see a lot of useful links. For example, the agenda of each day, and also some the lab materials, which I will talk about more in a second. And then there's also additional information about logistics, for example, where and when to take photos and everything. So in terms of the lab materials, you've already received a link from Elizabeth asking you to do some preliminary setups. And this is the web page, and these are the materials we'll be using throughout the tutorial. We will have this learning materials for you to go through, and each day you will have some exercises to complete. So you have these big chapters. For example, the first day will be the basics of running CESM. The second day will be some simple XML and modifications. The third day is nameless modification. And then there's diagnostic and challenge, which is not in this screenshot. But you will see that in this web page. So every day, our day is comprised of lectures and lab activities. For lectures, we have two different categories. The first one is component lecture, which is a little bit longer. These are about how the core model components work, including atmosphere, the ocean, the land, and every other model components. And there are also specialized talks, basically some very cool applications of the CESM. For example, we have Earth system prediction, paleoclimate, atmosphere chemistry, variable resolution, etc. And then apart from the lectures, we also have exciting lab activities each day. So as I mentioned, on day 1 and day 3, we will go through some basic steps of running the CESM. For these 3 days exercises, all participants will complete the same exercises. But then on day 4 and day 5, you have the choice to choose your focused area, and then work on, for example, on day 4 would be diagnostics, some diagnostic tools and some plotting scripts for you to practice how to look at the model output. On day 5 would be some challenge exercises where you can really dig in to make some advanced modifications of the model. So there's also lunch activities every day from 12 to 1:15 p.m. During lunch, obviously, you should get food. Food is available in the Mesa Lab cafeteria, which we will take you there if you can't find it. We have vegetarian and gluten-free options, and you are responsible for paying for your own lunch. And then we ask that if you can, please stagger lunchtime. So everyone, please don't show up at the cafeteria at 12 p.m. Exact. You can imagine the line would be really long. So if you can go a little bit earlier or a little bit later, that would be great. And then we have Meet a Scientist sessions, which are opportunities for you to have casual conversations with our staffed scientists. And these are very casual with no fixed agenda. And you should already receive the link to sign up for those opportunities. And we ask you to please fill out the form with your first, second, and third choice of your scientists you want to meet. And we will take a look at everyone's choice and try to assign one scientist to you to ensure a reasonably sized group. And then we also have Mesa Lab exhibit tours, as I mentioned at the beginning. So these tours are really cool. We have reserved private tours on Tuesdays and Thursdays where it's kind of exclusive for CSM participants. And then on Monday, Wednesday, and Friday, we also have public tours. If you couldn't make it to the Tuesday and Thursday ones, you're welcome to join this as well. And all of these tours take at 12 p.m. At the front door entrance. So if you're doing the private tours, we ask you to sign up in advance. But if you didn't sign up, you can also just feel free to show up as you want. And also, obviously, you can just explore the exhibit on your own when you have free time. So those are the launch activities. And a typical day of the tutorial, we will have start morning every day approximately at 8:25 a.m. We'll have lectures, we have lab sessions, we have light snacks and coffee just outside the seminar room. One note is that only cups with the lids are allowed in the main seminar room in here. And we ask you that if possible, please reduce waste and recycle as you can. And then lunch activity we just said, and then in the afternoon we have again lectures and the lab sessions and light snacks. This would be outside the Damon room, which we'll show you later again. And then at the end of the day, we all come back to this main seminar room where we all have this daily check-in. So this daily check-in, we will have a very brief discussion of what went well and what didn't for this day. And we also ask you to complete a very small daily survey. These surveys are about the daily lectures you received. There will be 2 questions. How relevant were the lectures to your own research interests or needs? And what's the difficult level of the lecture to fit your skill level? And if you have any other suggestions or comments. And on the very last day, there will be a general survey about your overall experience about the tutorial. So these are very important for us to improve the tutorial for future participants. So we really ask you to do this, and it's a big favor, and we thank you in advance. Yeah, so the theme of the tutorial is to learn. So there is no stupid questions. So if you have any question, please feel free to ask. And also note that we all come from different backgrounds. We have different levels of familiarity with the CSM model. So really, if you have any question, please ask. We don't want you to leave still confused or with your questions unanswered. And here are some basic information about the computer. If you need wireless, you will definitely need wireless access. Just use the UCAR visitor, the wireless Wi-Fi. You can just do a very short and easy registration and you're good to go. You're also welcome to use the EDU room if you have already have it installed on your computer. And then about the project and reservation queue, you should have received 2 emails, one from the Cécile help desk about your account username and password, and the second one from Elizabeth about instructions of first few steps of the tutorial. So these would be the theme of the tutorial one-time setup. So I know many of you were able to create the account and do everything as instructed, but I also know there were some problems coming up because some of the emails went to spam folder and everything. So if you had the problems, no worry. There's no need to panic. We will set aside bonus time for you to work that out this morning. So no worries at all if you haven't done that. And then for social, we have established a Slack channel, which already received a link to join. And auditors are welcome to join as well. Just ask us for the link. So on the Slack, if you browse all the channels, you will find the introduction channel. We encourage you to just introduce yourself to the other participants. And there's also like a social channel where you can organize the social breaks, the ice cream breaks and everything, the short hikes. Just for a fun time in general. And there's also announcement and a general channel where you keep up with what's going on with the tutorial. And on Thursday, we will have another social activity. That's the special CSM cafe. That will be in the morning where all the CGD staff, visitors, and also guests from across the NCAR lab will join us for a special cafe. So you can use this opportunity to network and meet with staff, ask questions, etc. Okay, there are the maps. You'll feel free to explore and you will find out where everything is. Most important thing is the cafeteria so you don't get starved. And then the main lab session happens in the library, which is on the second floor. We will point you to that when it comes to the lab session time. Other than that, if you feel like you need some quiet time, you can ask us for an empty room. And there's also a lot of outdoor seating in the nice tree plaza. And you're also welcome to take a little hike just outside the NCAR lab, a very nice little trail over there, which I highly recommend. And that's the end of my introduction slides. If you have any questions, you can ask. That's it. All right. I think I explained everything very well.
Did you draw that?
Oh yes, that's my art. I think NCAR is somewhere here. After all these years, anyone else? Yeah. Okay, perfect timing. I will give this podium to Dave Lawrence, our chief CSM scientist. Let me see if I can find your slides. Oh, that's not it. Okay. Wait, which user slide? Should be this one, right?
No. Drive.
Not everyone was downloaded. Okay, all right. Just a little.
The bottom one. Sorry. also. Okay. Great. Okay, sorry about that. Yeah, so welcome everyone, and thanks to Hui for introducing this, and also for our organization who's done, and Elizabeth and others who've organized this. You guys are gonna have a really fun week. This is always one of, I think, our favorite weeks here at NCAR, getting to interact with all the early career scientists, learning about CSM, and I think you'll learn over the course of the week how fun it is to use CSM in your research, and also how much the scientists here are so deeply devoted to this activity. I think that's kind of part of the allure, and hopefully you'll get involved in that as well. So if you're here, you most likely are well aware what a Earth system model is, but I'm just going to start at the basics here because I'm giving the opening talk. These are big models that are used to include physical equations to simulate key fields and processes in the atmosphere, ocean, land, sea ice, land ice, etc. Always a growing chemistry as well. Set of things. Processes that remain below the grid resolution need to be parameterized, and that's a big part of Earth system modeling. You learn more about parameterizations this week. That's essentially where most of the detailed effort is in to build these better parameterizations to make better models. And I kind of think of these Earth system models as syntheses of our understanding of the Earth system that are collected by thousands to tens of thousands of scientists around the world. These kind of represent, if you think of a pyramid of all the research scientists who are out there in the world taking field measurements or going on aircraft campaigns to satellite observations to building really high fidelity models, that all kind of builds up in a pyramid towards our system models, which sort of are lying there, relying on all that information that people have gained over the decades. So, this is what an Earth system model looks like. It's a collection of, typically a collection of component models. So you would have an atmosphere model that would maybe have a chemistry model attached to it, a sea ice model, an ocean model with ocean biogeochemistry attached, a river model, a land model, and more recently, things like a land ice model, so you can model glaciers and ice sheets. And these models are all coupled together with a central, it's like in our situation, it's called the hub and spoke architecture. So you have the centralized coupler, which is sort of controlling how all these models interact with each other, passing information back and forth, doing all the regridding that you have to do between different components of different grid resolutions, and also doing things like controlling what information is passed back and forth, and time step management, and all this kind of complicated stuff that has to go on. And then you also have a set of forcings. Depending on your problem, those forcings will be different, but a typical, say, climate change problem or historical climate, you would need to have information on what the greenhouse gases are, the anthropogenic aerosol emissions, volcanic eruptions, since we've observed those, solar variability, and other features of the Earth system that we can observe and we know have happened or we can project might happen in the future. So these models, they serve many purposes. They're there to gain scientific and mechanistic understanding of past observed events and changes. We use them to study recent past, present, and future, including projections, climate change, and their impacts. We use them to understand climate variability. It's really important to understand how the climate is varying and why it's varying when you're trying to study something like climate change. We can also use them to do subseasonal out to multi-decadal Earth system predictions or research into Earth system predictability, trying to understand where and when and how we can make skillful predictions. And especially with CSM, it's more used in a research framework rather than an operational framework that would then feed into something like the National Weather Service. And then, critically, it's used to provide actionable, societally relevant information so that people can make decisions about how to address Earth system variability on all time scales, to have make a better life for people on the planet, and also better life for ecosystems. And so you're all fully aware of this. Being in this room, I'm sure you're aware of this. But the Earth system models have formed the key basis for all the IPCC reports. And really, without Earth system models, we wouldn't be able to be so definitive in our statements about climate change and what's happening. But because we have these Earth system models combined with Earth observations and our scientific understanding, we can say, that it unequivocally that climate change is happening and that it's, mostly due to humans. So, they've been pivotal in all this. So what is CSM2? Or CSM, so the Community Earth System Model. So the version that is our operational version right now, which we're using for science, is called CSM2. This is the configuration that was used for simulations in support of the Coupled Model Intercomparison Project 6, CMIP6, which is the set of coordinated simulations that our groups have run. Different modeling centers around the world all run in a coordinated fashion that then feeds into or is used. A lot of those simulations are used in the IPCC reports, but we use them for all sorts of scientific understanding. And many other large community simulations that you hear about this week, for example, the CSM2 Large Ensemble, which you'll definitely hear about over the course of the week. So these are the component models. You'll be hearing about these models in detail throughout the week, and be hearing also about the next generation version, which we're working on right now, and I'll get to in a minute. But it's like I showed, this hub and spoke architecture, and we have all these different components. So one I didn't mention previously is surface waves, which is also a component model within CSM framework to calculate ocean waves. So, there's many Earth system models around the world. There's, if you look in the IPCC report, you see like 40 plus submissions. Sorry, in CMIP, you'll see 40 plus submissions. There's roughly 10 or so I would call big models around the world with big efforts that are, on the order of the same scale as CSM, and then several other models that are derivatives from those. CSM has some somewhat unique features, and I think it is fair to say it's one of the leading models for studies of climate change and climate variability. It's got a long legacy. It was one of the first models out there. We had a nice workshop a few weeks ago. Some of you were there, the CSM annual workshop. It was the 30th annual workshop, and we got to think about the 30 years of development as our 30th workshop. So these have long legacies. These are not small pieces of code that you write on your in Python over the course of a weekend. These massive efforts, and it's kind of calling card is we call it a true community model, where we really provide we do community development. So we would take input from scientists all around the world who say we have a better idea about how to make a better model, and so we take that on, and when it is a better idea, then we include in the model, and hopefully some of you here will become future CSM developers. That's one of our goals in giving this tutorial, is to build the next generation developers, and we also provide support, and that's part of it is things like this, the tutorial. Part of it is we have a forum where you can ask questions, a user forum that is really widely used. We have many opportunities for visitors, and I'll get to and for other ways of engagement. So we really do think of this as we are providing a tool that enables the research community to move and do their science. We've got strong community participation with over 2,000 plus researchers on our mailing list, and hopefully all of you are getting signed up or have been signed up for our mailing list. It's really quite widely used. It's hard to really quantify. We're always trying to quantify it, but just as an example, I don't know how many of you have been to AGU yet, but it's this massive meeting, and you go to AGU and you will see CSM throughout the meeting. Over 400 talks at AGU 2024 included CSM. That's probably a severe undercount, as many talks don't talk about CSM in their abstract or their title. And it's just a huge model, 4.5 million lines of Fortran code, and so that's upsetting for most of you. But this is a long legacy. We have talked about trying to convert it. It would be a massive undertaking to convert it into another language, and we probably will be doing some conversion over the years, but a wholesale conversion into some Python-based thing is just not really practical. And it's got over 1,000 geophysical variables that it spits out. You can basically look at anything. If you can think of a thing to look at in the world, it's a good chance that CSM is simulating it. And so then just a final in the introduction here, I like to just think of it as a virtual laboratory. So you're going to learn about the basics of running CSM, but really, your research is going to be only limited by how creative you can be about how to use it, right? So this is a way you could get to, essentially control Earth. Say, okay, I want to spin the Earth twice as fast as it is right now and see what happens. You can do that kind of thing. You can change the continents. You can turn off different parameterizations. You can run with different components, and I'll get to this in a minute. So it's really a research tool. In some ways, the least interesting way to run CSM is, and it's like just out of the box configuration. It's what you do with it and with your creativity. And so you can look at all these different things: air system variability, air quality, biogeochemical cycles, et cetera, et cetera. So really, as you're going through the week, be thinking about the creative ways you could approach your scientific problem using CSM. And so just to sort of hammer in that point, CSM supports quite a wide range of climate science and really Earth system science through a single model code base. And we've really worked quite hard to make it easy to use and easy to configure in these many different ways that lets you set off on what at least it's a starting point for your own research. And so this is the configuration that we might run for a CMIP level simulation where everything is turned on. It's quite a complicated model. It's also very slow and computationally expensive. And so it's unlikely that you would be using this configuration that much in your research because it is such a hard configuration to run, but you might be using the output that we produce that we make publicly available. But you can make lots of different decisions. If you're an oceanographer and you just want to study oceanography processes, you can run in a configuration with a data atmosphere where you're forcing it with reanalysis products or some other observed forcing and running it through the same system, only changing a couple of switches in the code, and you can run with just the ocean and the sea ice. And the data atmosphere is going to have all the forcings like temperature, precipitation, solar radiation, long wave radiation, humidity, wind, CO2, et cetera, from observations. If you're an oceanographer who cares about biogeochemistry, you might turn on the biogeochemical model. It's going to cost you a bit more, but you can study things and then possibly link it into a fishery model. We actually have a fishery model that can lightly couple to CSM. If you're maybe a terrestrial scientist, you could also run the same kind of thing, data atmosphere with the land and just the rivers. And so you're, again, just forcing the land with observed data. It needs to change. And then each component model will have a set of options within it. And here's just a short list in the land, and I came from the land community, which is why I kind of lean on this, but a bunch of different options, and you can choose. So you might say, oh, I actually don't care about land use change, or I want to know what happens if there wasn't land use change, I can turn that off. Or if I want to study the biogeochemical cycles, I can turn that on. If I want to study crops, I can turn that on or off. We have prescribed vegetation mode. We can look at ozone damage, methane emissions. We can also do structural changes. We can change the number of soil layers depending on what your question is, or you might be interested in paleoclimate and you want to get rid of humans completely, and you can turn off humans by just setting the no anthro flag. And so just an example that each one of these model components is going to have options, literally 10s to 20 to 30 to 50 options within them, and that's part of your science, is understanding which options are important to you. And then just the final point here is to kind of spread it out across all the domains. We also can turn on different. Maybe you're interested in land chemistry interactions, atmospheric chemistry interactions mainly, and so you could set up a configuration that looks like this, where you're running with a coupled land and atmosphere, where you've turned on the chemistry model, and there's all different levels of chemistry representation. So maybe you have an air quality question, you might go for a really complex chemistry mechanism, and you're interested in the BVOCs that are coming out of the terrestrial vegetation and understanding how that all creates ozone and things like that. So again, just a really complex code base that allows you to do a lot of things. Okay, so Earth system models and data can be a tool in your research toolbox, but Earth system modeling is hard. My postdoc supervisor, many moons ago, told me when I was struggling as my first days and years being an Earth system modeler, he says, and I was doing a lot of simulations and getting essentially nothing that was really useful out of any of them. And she goes, don't worry about it. And she was a very famous scientist. She said, don't worry about it. It takes 5 years before you become a useful Earth system modeler. And I thought, oh, that's ridiculous. Come on, I can be faster than that. It's not true. I mean, obviously you can do something that's useful. Don't get super depressed. But it takes time from when you first start learning and you get the skills to build up the knowledge and the understanding of this complex set of things that are going on, to when you're able to use the model for real, new, innovative, edge of understanding insight. So I think it's normal for it to take a little while. I think that's just an important thing to keep in mind. So this week you're going to learn about the component models within CSM and the science behind them, how to set up, run, and make simple modification to CSM, and some ways that CSM is being used to address some of the science questions that we're interested here at NCAR and with our community. But that's really just the beginning. Learning how to usefully apply Earth system models and Earth system model data to answer research questions, it never ends. My advice here is be creative, acknowledge that there'll be missteps, and have fun. So hopefully you get that spirit kind of at this meeting. Okay, so I want to just kind of take a step and say, how would you start thinking about, if you have a scientific question, designing the set of experiments you might run? And so this is a slide we like to show pretty frequently to indicate that as you're setting up to work on a research question, it requires different considerations. And often the three fundamental ones you have to decide near the outset is what is important to you for your research question. You have options to go for either high resolution, which is going to cost you more, high complexity, a high complexity model is going to cost you more, or you might need large numbers of ensembles where you run the simulation many times, or some combination of these. And each one of these is going to be essentially a computational resource and time decision. And you're going to have to be able to figure out how to merge all these things together to decide what is the most efficient way to get to your science, to answer your science question. And so, the complexity realm, I've already indicated we have all these models that are coupled together, but it hasn't always been like that, component models. We started off in the 60s and the 70s, it was just, atmosphere, very simple atmosphere, very, very simple land, and ocean models were coupled together in the late 70s, early 80s for the first time, first couple of climate models in the 80s, and then really coupled climate modeling didn't really begin until, the 90s or so. And then as we went out in time, we've been adding complexity where we might add interactive vegetation, biogeochemical cycles, aerosols, ice sheets, marine ecosystems, the upper atmosphere, atmospheric chemistry, et cetera, and things keeps getting added, and I'll come to a moment how AI and machine learning are folding into all of this. The other axis is ensembles, and we found here at NCAR that the utility of large ensembles has sort of been a game changer in our understanding of what is the internal variability or the natural variability of our system versus the forced trend due to greenhouse gases, particularly important for the climate change problem. But of course, ensembles come into weather forecasting and seasonal prediction, all those things as well. And what we just show here on the left is, two simulations, the results at near 2080, 2100 or so, and the wettest simulation and the driest simulation in terms of the change in precipitation. And you just see it's a massive difference between those two different simulations. And so we now run the model regularly when we have new configurations 100 times to see what that variability is across all those different simulations. And that's the sort of the natural variability. You can't reduce uncertainty more than that. But you see the average trend is there on the right, the winter precipitation trend. You see that's a fairly clear signal that it's going to get wetter across most of the US, except for maybe the Southwest, at least in CSM. And then the last one is resolution, and this is an very old figure now, but the resolution cost goes up very dramatically because you have to change not only the grid cell resolution, so the number of cells you're representing, but also the time step usually has to go down, and so everything costs more. And so if you go from our global roughly 1 degree simulation, which is what we use for CMIP6, to our kilometer scale version, which is a 3.75 kilometer scale version of just the atmosphere and the land, it's a 25,000 fold cost change. So, that's not really practical for almost anybody to do that kind of resolution. So these are the decisions you need to make, and we have regionally refined capabilities and other ways to deal with resolution that you'll learn about this week. Okay, so this was CSM2. We are working towards CSM3. That's one of my main jobs, is to help our team here build the next generation model, and we're going to see significant updates to all the different component models. So, if you're looking carefully, you'll see the numbers increment by 1. That doesn't mean too much to anybody. On our website, I forgot to put the link here, we do have the full list of 50 plus things that have been updated across the CSM component models that'll be going into CSM3. So we are, striving and struggling to get a good-looking model together so we can release that to the research community, hopefully in early 2026, and use that for CMIP7. And this is a couple of selected updates that I'm going to, I think, skip over in the interest of time, because these may not mean that much to most of you at this time until you kind of gotten more of a peek into what the models are doing. Okay, and then in my last 10 minutes or so, I kind of want to talk about some of the forces that are driving the future of Earth system modeling. I think this is a pretty exciting time to be involved in Earth system modeling. The questions have largely somewhat changed, and the opportunities have grown in terms of Earth system modeling. And so, if we went from the beginning, not the beginning, but early days of Earth system modeling, we were trying to understand, was climate change really happening, and was it due to humans, and what were the main feedbacks in the Earth system? And what are the feedbacks is still an important question because we don't have those all pinned down exactly, but we have essentially answered the question about whether climate change is due to humans. But what's needed now is there's an urgent need for actionable climate change information on the climate risk, consequences of intervention and mitigation. And so, in this actionable information is really critical. And the fundamental question is, I like to put it with this set of slides that fundamentally comes down to where and when will people and ecosystems experience more extreme events? Will we have enough water or maybe too much water? Will we be able to grow or harvest enough food from the land or the oceans, and can we produce that food sustainably and not add to the climate change problem by releasing greenhouse gases into the atmosphere or degrading our land by destroying our soils, things like that. And also understanding how there is still a need to understand whether or not we're getting the climate change right. And if you want to need this actionable information, you need to start looking at more of the details of the climate simulations that we're simulating, and whether or not we're simulating the trends correctly. And this is a nice paper that that just came out that I would recommend reading if you're interested in this at all. That confronting your system model trends with observations. And there's enough. The record is long enough now, and we have enough observations with a long enough record that we can start asking the question, like, really in fairly detailed ways, are our models able to reproduce what's going on, what has gone on in the Earth system? And from the broad perspective, like the temperature change, we're getting essentially right. We're getting spatial patterns of temperature change fairly good, with some exceptions. We are able to simulate things like shifts in jet positions, relatively well in some things, but then other things we're not simulating well, like we're not simulating the trend in humidity over semi-arid regions at all. Not a single model gets the sort of relatively flat trend in humidity. Our models are projecting it would go up and have big implications for forest fires and things like that. And so this is a nice paper. It sets out about 40 of the major trends that we are thinking about, or we have some observations of in the Earth system, and asking whether or not our Earth system models can reproduce them. I think it's a really cool paper that helps us understand what the potential impacts will be on humans, because that's if you're not getting your shift in your jet position right, you're probably not getting your change in extremes right as well. Okay, and then also we're using them to study. We need to use them to study the potential consequences of climate intervention. Unfortunately, if we cannot get a hold on our greenhouse gas emissions, there is some probability someone around the world is going to decide that we need to intervene and do things like solar radiation management, or sending aerosols up into the atmosphere. Obviously, geoengineering is super concerning and stressful, but we do feel like it's important that if anyone's going to think about doing this, at least they go into it with information, or we have some understanding. And so that's a big feature, big important area of research. Also, carbon dioxide removal. If we're going to remove CO2 from the atmosphere, we need to know whether or not that CO2 is going to stay. Where are we going to put the carbon is a huge question for us. Reducing emissions on one hand is one way to get to low climate change targets, but the reality is it's going to take more than just reducing emissions, and some of that change is going to have to come from us pulling CO2 out of the atmosphere, either in the land or the oceans. And if we do that, is it going to stay there? Obviously, if we pull carbon out and put it into a forest, and the forest burns, you haven't really gotten anywhere. And Earth system models are great tools to help us understand the suitability. And then you still need to use these models to understand the potential and the probability for tipping points. So there still could be some unanticipated tipping points out there in the Earth system that we have not yet fully understood. We have definitely identified some possible areas where things could be a tipping point, but Earth system models need to continue to look at it as they get better and better, keep exploring and evaluating, so that we have some forewarning, hopefully, if there is some more severe tipping point coming. And I'm not saying this is a tipping point, but we just had this like crazy warm year in 2024, setting records that were just blowing things out of the water in terms of our understanding. And so it's an open question. Is that evidence that there's some tipping point is happening? Is it just internal variability? Is climate change accelerating? The Earth system models are tools that help us understand that. So to answer all these questions, I think we need to evolve our models, and there's a lot of people making lots of different statements about what's the best way and where we should put our effort in. It's a big debate going on in the Earth system modeling community, but in my opinion, it's going to be sort of all of the above. We are going to need to push to high resolution, and we found some strong benefits of going to high resolution. Definitely at 1/4 degree resolution atmosphere, 10th degree ocean is a configuration we have, which we find has really nice features compared to our 1 degree resolution simulations. And there's also groups around the world, including us, that are pushing towards what we call kilometer scale, like really, really high resolution, where there's some parameterizations you can remove, like convection parameterizations. And that's nice. Whenever you can remove a parameterization, that should lead to better simulations, although we're finding it's hard to get a good global kilometer scale modeling configuration because it's just so costly and it's hard to tune. Machine learning and hybrid modeling is coming, as I'm sure, and emulators. It's a big part of what the thinking is. I'm sure you guys are all probably involved in using machine learning in some of your research, and how do we use that to advance our Earth system models. And there's more emphasis on Earth system prediction and predictability across a range of timescales. So we've kind of done the climate change problem to a certain degree. Can we advance S2S, S2D, and 30-year projections, or out to 30-year projections? There's changing computing architectures and languages, and the need for code modernization, as I already mentioned. And then there's calls for improved accessibility of Earth system models and Earth system model output, especially to the global south, which are most impacted by climate change. Typically, people in the global south are most impacted by climate change and are least involved in climate change science, and that is not a great situation, right? They should be involved in some of the decision making about what we're going to do to address it and understand what's going on. So these drivers present many challenges and opportunities for the CSM activity. So we are working on all of these. We have this high resolution configuration of a 1/4 degree atmosphere and 10th degree ocean, which I think you'll hear about this week. We're developing a CSM3 high resolution version. We didn't put one together for CSM2. We also have these activities called CSM Earthworks and Storm Speed, which are projects developing the kilometer scale configuration, which is looking pretty cool, although very, very expensive. Like I said, 25,000 times more expensive than the 1 degree. And we also have the option to run with regionally refined grids, where you can telescope in a particular region to get higher resolution. And that's another nice way for much less computationally expensive way to at least have resolution in the area of interest for your project. And we're increasingly able to support these regionally refined configurations. We're also working on a hybrid model. We're calling it the CSM3 MLE, Machine Learning Enhanced version of the model. We're taking advantage of 2 big projects, LEAP, it's the NSF Science and Technology Center, and also M² Lines, which is a SMIT Futures supported activity. And the idea here is that we can build, taking advantage of new machine learning algorithms combined with high fidelity models and a huge range of Earth observations, and build new machine learning based parameterizations and new machine learning based parameter optimization methods to build what we are saying our next generation ESM with. We're hoping to have more accurate projections. And there's some evidence that this is going to work, and we just had a workshop last week on implementation to try to move that forward. So we're hoping that with these machine learning enhanced models, we can have a leap forward in the reliability, utility, and reach of climate projections through this synergistic data science and climate science. And then Earth system predictability across timescales. Fundamentally, we're trying to understand all these different kinds of events and whether or not we can predict them and in what timescales we can predict them. And Earth system models, with their big range of model complexity, are great tools to help us really push down and explore, the wide range of variables that we might care about in the Earth system in terms of predictions, extending beyond just the standard fields of temperature and precipitation, extreme wind events, and things like that. So finishing up here, we have these working groups that we use to sort of organize our activity. So there's 12 working groups in CSM, and hopefully you will find a working group that you're interested in getting involved with. It's totally open process. There's no application process. You just show up and you're part of the working group. So there's about 2/3 of these working groups are what we sort of term as model development working groups, where they have some responsibility for developing one of the component models within CSM, but they also have a lot of science activities within them. And then we have 4 working groups that are mostly focused on applications. So the biogeochemistry, climate variability and change, Earth system prediction, and paleoclimate, focusing on just the application of CSM. And so really encourage you to get engaged. There's many learning and engagement opportunities. There's the tutorials like you were doing here now, which there's also tutorials at AGU and AMS. If you go back and have any colleagues and you say you say CSM is so fun, you should learn about it, they can look for tutorials at AGU and AMS. We do a lot of mentoring. NCAR CSM staff hosts graduate students, postdocs, and faculty visits all the time. You guys are here this week. It's really exciting, but all summer, if you are here, some of you are staying here for the summer, you see how active it is with all the students and faculty and postdocs who are visiting. And then we have lots of workshops, or not lots, several workshops. The big one is a CSM annual workshop that occurs every June, about mid-June. We had the 30th annual workshop last year. And then there's the winter working group meetings, which typically in February or early March or late January. If you're on the mailing list, you'll hear about them. And that's a really great way to come and learn about the cutting edge science that's going on with this CSM that's more targeted towards your particular field. I think it's in some ways one of the best opportunities for graduate students because you really get to have a bit more time to interact with some of the scientists here at NCAR and across the community that are using CSM. Whereas at the CSM annual workshop is a bit of a, whoa, that's kind of a lot. It's also a great way to learn is when you sort of take on too much information, but it's quite a big meeting. So that's it. I can stop here and take questions, but really I just want to welcome you all to the CSM community. Hope you have a really fun week. I'm sure you are going to have a fun week. This is going to be a blast. So thank you.
Okay, questions for Dave?
A question about model development. In that process, do you do parameter ensembles, or how do you learn about what parameter values to use in standard configuration?
Yeah. So historically, we did not really run many perturb parameter ensembles because they were quite expensive. But in the last 5 years or so, we've actually started relying on them quite a bit. And so, especially within this hybrid modeling framework, we've sort of been building up the tools to regularly run parameter ensembles for the atmosphere and the land. In the atmosphere, it's going well. On the land, we were able to take advantage of some acceleration methods that we came up with over the last couple of years. Allows us to run really fast to get through the spin-up. We have a spin-up problem on land with biogeochemical cycles. We had some discussion last week about this, and the ocean is thinking about something as well. So we do have this capability. My goal is that we get a bunch of these tools in place to release with CSM3 so the community can either use the ensembles that we've already run or run their own if they have the computational resources to do it. So, there's lots of different ways you can try to calibrate. We are using machine learning based tools, emulators, and things like that. It's a really rich area right now in nervous system modeling. But historically, we would hand tune a lot of the time, so expert judgment. Sit around the room and someone says, well, I think this parameter should probably be about 15% higher. Let's try that. And it's really painstaking. So we are pushing towards this. And essentially, we're not the only group that's just, everyone is hand tuning. So it was like, it's such a complex model. So we still do that, unfortunately. And we will do that for the foreseeable future. Oh, just one more thing about that. When it comes to coupled model tuning, that's a whole other thing, which really at this point, we do not know really how to deal with because the coupled model is so expensive. So hopefully one of you guys are going to figure that
out. You showed that infographic with the components of the model growing with time.
Yeah.
Looking into the future, will there be a need for more components of the model? If so, what?
Yeah, it's a good question, and none of the future things I mentioned were like focused on complexity. I don't feel like there's like a big one. I think if there was one that I could foresee happening would be to bring in like some sort of social dynamics model into it, like trying to model how humans are working. So either we had a nice talk at the CSM workshop where we had coupling in with the climate intervention problem. I think it's kind of interesting to say, let's couple in a model of societal dynamics, which is sort of accounting for the weirdness that you can have with governments or rogue nations or something like that. And then let the model kind of go and make, if you're interested in climate intervention problem and say, okay, it gets too warm, some humans on the planet decide you're going to try to cool the planet off, and whatever it is, some country decides they're going to launch stuff into the atmosphere, and then you get some wars that happen and whatever, and then people say, oh, it's not working, let's not do it, or it's not working, let's triple our effort, or things like that. I think that'd be super fascinating to see what happens, the chaos and dynamics. So I think there is some chance it will involve social dynamics at some point. In terms of the physical system, I don't think there's like super obvious things that are missing. There's going to be things around the edges, and I feel like more of the work is just going to be on making what we have better, faster, using machine learning or higher resolution, or removing parameterizations by going to higher resolution. But I'm totally happy to be wrong about that. There could be something I'm not thinking about. But
With what we're learning this week in CSM3 being released next year, are there aspects of the tutorial that we'll have to sort of like relearn or update after that is released, or is that going to be all applicable?
I think the main stuff that you're going to do is going to be the same. So it's going to be the physics and the biology and the chemistry that'll be different. So there really shouldn't be much, if anything, new you would need to learn. Wei can confirm that right there. We're using essentially the modern code base. So CSM2 is essentially embedded within the same code base that we're building CSM3. So that's the way we always do it. So you could, within the code base that we release, you would be able to set it up like CSM2 or CSM3 with all this, so it's just a set of choices you make as you set the model up, and then you would use all the same tools and commands and everything you're gonna learn this week. So no, we're aware that could be a problem, and so we're trying to.
You're also gonna get a taste of CSM3 in one of the diagnostic labs on Thursday.
So you mentioned like machine learning, like going like in future model development, and I was wondering how important it is for like early career scientists to have a background in machine learning, like, and how like kind of mainstream will it become in future model development?
It's a huge part of the conversation now, that's for sure. I do feel like it's most likely it's going to be helpful to have some machine learning knowledge. I also will caution and say it hasn't changed, fundamentally hasn't changed what we're trying to do. We're trying to have scientific understanding of how processes, at least in nervous system modeling, how processes interact. And so there are some, it's a complex topic, but there are some people who are saying we can learn maybe the whole Earth just from observations, and build a Earth system model that's built just from learning from observations. But my feeling is you would have a hard time using that to understand what the Earth was doing. You might be able to reproduce what the Earth was doing, but then to probe in and understand what's going on, that's going to be much harder. And so I feel like I would caution people from moving like all into machine learning and losing the ability to have like physical, rational understanding about how the physical system works. And so I feel like we're in a bit of a gold rush boom right now where people are like chasing the things about machine learning. And I feel like that's actually going to, this is very personal, that we're going to it's going to be like, we're going to pass that sort of phase of like boom, and then come back to some more reality, like, okay, now how are we really going to use this to advance scientific understanding? And a lot of times it's going to come back to like, actually we need the physical parameterization or some understanding of it coming back. So I will say as a chief scientist, it's a complicated, confusing time right now. But I do think it's pretty exciting as well. So I don't know if I really answered your question, but.
Given that there's going to be an update with the ocean model especially, going from POP to the MOM, what's going to be the teaching philosophy this year? Are we going to be simply focused on POP and then, not talk about MOM at all, or like what's the idea behind that?
I don't fully know what the lectures on the ocean are going to be, so I haven't looked at them. My guess is they're going to touch on MOM at least, and a lot of the stuff is the same, right? If you fundamentally, a lot of what you're including in the model is the same, and then it's sort of at the details, which may be something you really aren't going to learn this week. That understanding all the different coordinate choices in the ocean is like complex and. Probably not the thing you want to learn in a 1-week tutorial, but those are the things that are different within MOM compared to POP, your choice of vertical coordinate. A lot of the parameterizations are the same, that we moved them over from POP to MOM. So I don't 100% know, but if you have questions, the scientists who know are here, and definitely find them during the week and ask them about how to, if you have any questions, and then what following up later if you find questions.
Given the current socio-political climate, is CESM planning to fully participate in like CMIP and the IPCC reports?
Yeah.
And so on?
It's an excellent question, or I don't know if it's an excellent question, it's a difficult question. We are thinking about it very carefully. To be blunt, there's risks of doing it, there's risks of not doing it, and we had a big discussion at the CSM workshop with some of the leadership teams there, and our current plan is to proceed like as if we're going to do CMIP. We're not at the stage yet where we can run CMIP, so we sort of don't have a decision to make. But we're proceeding to push as hard as we can to get to that. And if the one area that you might have some doubt, I mean, I think of running the historical simulations and it's called the deck, if you're familiar with it. It's like the core set of simulations helps you understand your system model. I don't see, like, there's no reason why you wouldn't run that. So it's only the scenarios which you might have any question about. We could, for example, choose not to run the high emission scenarios. We could also choose not to run them, and we won't have to decide it for at least a year from now. It's probably so. Anyway, we are thinking about it very carefully, yeah. It's a tough question.
So you mentioned climate intervention a little bit.
Yeah.
This is a growing but also very controversial topic.
Yeah.
I want to hear what's your thoughts or opinion on it.
Obviously, my thought is we should reduce emissions and not have to do climate intervention. In terms of doing climate intervention research, I know there's some people who feel like we should not do climate intervention research even, to not even open that door at all. I guess my perspective is that's probably, there's debate, there's no right answer on this. My personal perspective is that I think we're better off having done the research and hopefully identifying where especially if there are any major issues with it, that we have some forewarning about that, and then we could be campaigning against it if we saw major issues. If we don't see major issues, then I guess that's a little bit of an authorization for we should do it. It seems totally crazy to do it. It also depends on what climate intervention research you're talking about. I think research, we kind of put carbon dioxide removal into climate intervention because that's a specific human action to change the climate system. And I think that research, 100%, we should be doing full speed ahead because we need to be thinking about ways to get carbon out of the atmosphere. And that may have climate consequences, but that's a consequence I think we should be at least considering doing. If it has super negative consequences for the ocean ecosystems or for land ecosystems, then we would have to consider whether to do it or not. But I think that kind of research is 100% should be done. And I will say also, when we get involved in it, we try to get involved in a way that will help us advance our model. So if we get a project supported to do climate intervention research, we say, okay, well, we also want to get funding in that's going to help us build a better aerosol model. So we have just a better aerosol model in general, which we can then use for climate intervention research or any other research. Because finding money is always an issue. Support. You guys are asking hard questions.
More hard questions? Okay, if not, let's thank Dave again.
I'm just going to be around here through Tuesday at lunchtime. I'm going to be one of the meet scientist people. If you want to try to catch me, see me at lunch or in a break today would be the time. Otherwise, I'll be gone from Tuesday at lunchtime on. So, but enjoy your week, have fun, and yeah, thanks. Welcome to the meeting.
Okay, welcome everybody. My name is Peter Lauritzen. I'm a model developer here. We're really excited to have you here for this year's CESM tutorial where you get introduced to coupled Earth system modeling. And in my opinion, a lot of the questions we need to answer for society, you really need a coupled Earth system model. All the way from predicting heat waves, sea level rise, down to giving data to insurance companies of what your premium should be on your house or your car and stuff like that. Dave, I hope, I didn't see his lecture, but I think he introduced the different components of an Earth system model. So we divided into atmosphere, ocean, land, ice. dynamic ice sheets, if that's included, etc. So you're going to have 2 lectures here on the atmospheric component, because we divide the atmospheric component into 2 parts that I will define in just a moment. So we're in the business of global modeling. So here's a satellite image from NASA showing outgoing long-wave radiation. It's global modeling, so periodic boundary conditions in the horizontal. And if we wish to build a model around this, the first thing we need to do is to introduce a grid. We need to discretize our system. You can do that in many ways. I've just, for the sake of simplicity, showed you a latitude, longitude grid right here. After we've defined our grid, that immediately defines the grid scale of the model. So typically for large-scale model run for centuries, the grid cell size is about 100 kilometers. On this grid here, we solve the resolved scales equations of motion. So those would be your approximated Euler equations. So those are the governing fluid dynamic and thermodynamic equations. So we solve that on this grid here. It's very important to note that our models are not accurate at the grid cell size. So that means you can probably not trust your 100-kilometer wave in your model. And I'll return to this in just a moment because it's pretty important. In modeling jargon, solving these governing fluid and thermodynamic equations is referred to as the dynamical core, or just DI-core. However fine your grid is, there will always be stuff going on. The subgrid scales are not represented by your equations of motion, either in terms of not having the process described, such as phase changes, radiation, or you're just not running at high enough resolution, so you're not resolving small-scale gravity waves. So there's always stuff going on below the grid scale. And what is done in a large-scale model is, inside each of these grid cells here, we have our prognostic variables. They can vary by model, but you always need to know which way the wind is blowing. So you have the zonal, meridional components of the wind. You'll have a temperature or potential temperature in each grid cell. You might have pressure or density in each grid cell, and then you'll have the average of whatever chemical constituents you have in there, and all the forms of water in the atmosphere. So the gaseous component of water, so water vapor or condensate, such as ice and rain droplets and so on. The job of the parameterizations here is that we give it the resolved scale, and then that has to figure out what's going on subgrid scale and how that impacts the large-scale flow. That's an extremely hard problem. There's an entire lecture devoted to that this afternoon. Parameterizations we usually just refer to as physics, or sometimes we even refer to as column physics, kind of emphasize that the parameterizations usually only operate in a column. There's no communication on the sides. We are reaching resolutions where that's not a good assumption, but it's a technical difficulty to do MPI communication on the physics side at this point in time in global modeling. Alrighty, so we have the dynamical core, we have the parameterizations. Those two need to be coupled together. This is a pretty technical subject. There are not that many papers on it, but it's pretty important. So just to give you an idea of what it could look like, so I'm taking the example from CESM, or the atmospheric component CAM. So the first thing we do in that model is we define the state on the resolved scales. We pass that to our physics suite. And the physics suite here will contain a series of parameterizations, so shallow convection, deep convection, radiation, microphysics, unresolved gravity waves, surface drag, all these kinds of things. And those can be coupled in different ways. So what we do is we run one parameterization, update the state, and then we provide the updated state to the next parameterization, and so on. That's called sequential split update. And then within parameterization, there might be some complicated splitting happening as well. I won't dwell on that. I just want you guys to be aware that that's in the model. Then once, or halfway through the physics suite here, we talk to the surface components. So the atmosphere will tell the land and the ocean that are below us, how much rain is falling out, snow. And then we will get from the ocean, like what is the sea surface temperature, or the land will tell us how warm is the surface, and that's communicated up to us in the atmosphere. And then we run the other part of physics. And then after all that physics is done, and then we will have the accumulated physics tendencies. It will tell you how much will the wind change, the temperature change, how much will your traces change, etc. And then it's the job of the dynamical core to add these tendencies to its state. And again, there's a lot of choices to be made there. And over the right-hand side here, it's just an example from the spectral element die-core that we're using for CESM3. And in that die-core, the first thing we do is we give a part of the physics tendency to the die-core, and then we start running the actual dynamical core. And in here, there can be various forms of subcycling, etc. Won't go into details. If you're interested, you can see this paper here. Alrighty, so let's take a step back. When you have to build a model, you have to figure out what you want to model, what's important to represent in your model to create a credible atmospheric model. So here's a simulation from a model developed here at NCAR called MPAS. It's run at 3 kilometer resolution, so really, really high resolution. I think if I showed you an animation of a satellite image, it would pretty much look the same. And you can see there's a lot going on here, as represented by the long wave outgoing radiation. So one important thing is, in each hemisphere, you have these large undulations in the jet stream happening above these cloud systems here. They have time scales of many, many, many weeks, and they are like 10,000 kilometers across or something like that. Then below that, you have cyclones and anticyclones forming. So these are about 1,000 kilometer in scale or so, can last for weeks. And then at the very front of these cyclones here, you have areas where the warm and cold air collapse and you generate fronts. They're about 10 kilometers across or something like that. Let's see if I can play that again. And then you have convection. So convection can be organized on a huge variety of both time and space scales. So in the tropics, you have these very massive systems developing here that are like thousands of kilometers across. Over land here, you can typically have these small-scale cumulus clouds, forming due to turbulence in the boundary layers. So water vapor lifts enough to condensate. These can happen just on a daily, hourly time scales, and you have all the way to thunderstorms, squall lines, and whatnot. So if we want to build a credible model, we need some kind of representation of these phenomena and others. So here's a space-time representation from John Thuburn from a lecture he gave at this room a long time ago. So you have horizontal scale all the way from meters here to thousands of kilometers. On the Y scale here, you have from a second up to a seasonal time scale. And then on this line here, you pretty much have all these phenomena that I just described. So one thing that's important to note here that you can also see from the image here is that phenomena in the atmosphere appear as a continuum. There's no spectral gap. There's no such thing as a cyclone is 1,000 kilometers across and that's it. It will never become smaller or larger than that. So that makes modeling really, really hard because we have that interaction. And the reason why it's really hard is we need to define a grid scale. So as I did on the first slide, so this is like 100 kilometer across grid scale depicted on this time space diagram, and we have a physics time, so about half an hour. So this is pretty much what we can resolve in that system. Everything else here more or less need to be resolved by or represented by the parameterizations. On this plot, you also have fast waves shown. So we have gravity waves here. So typically when the atmosphere gets out of balance, so let's say you have deep convection happening, there's a lot of heating being released. Sometimes on radar images, you can see gravity waves propagating away. That's the atmosphere trying to get into geostrophic balance again. Those are very important wave in the system. And then we also have acoustic waves if your equation set allows for it. The reason why I'm showing them here is they're fast waves. Fast waves determines, in general, the longest time step you can take in the model for it to be stable. So they can be very restrictive for your time stepping. The shorter time steps you're taking, in general, the less efficient your model is. So one of our limitations in our model is the time steps are pretty short, so we can't run as fast as we would like to. So there's a lot of work going on across the world getting to really high resolution. So we have a version of CAM running at about 3 kilometers resolution, and the time steps are down below the minute. That's shown with this, this red line here. Now you see we're starting resolving more and more stuff. So we're getting really close, but we're not there yet to actually resolving convection. So we call these convection permitting models. So here's an example from CAM-MPAS simulation done by my colleague Adam Harrington. On the left, we turn off the parameterization for deep convection. And on the right here, we have a deep convection scheme on. You see, they look pretty similar at northern latitudes, but when you get into areas where a lot of deep convection is occurring, you see that we have a lot of spotty behavior. So usually this will develop into these large convective tropical systems. And you see when we have the convection scheme on, that starts happening. So this resolution, you still need deep convection, but we're slowly getting there where you don't need to have that parameterization. And that's pretty exciting that that's happening because it's a big uncertainty in our models. So when you have to design a model, you have to figure out what do you want to use it for. Like we'd all like to run full complexity, 1 centimeter resolution, but we can't afford it. So we have to make some choices. So are you doing numerical weather prediction? Are you just running 10 days? Are you going to run 100 years? Do you want to resolve squall lines, tropical cyclones, supercells, or maybe not? What kind of chemistry? Are you doing chemical forecasting? Are you doing aerosol indirect effects? Do you need to resolve the stratosphere? Do you want to predict the weather for satellites, doing space weather? CSM can do a lot of these things. So that leads to making choices. So you have to choose an equation set. And I can give you an example of what is done in our current version of the model for mainstream applications. So we take the compressible Euler equation and we make a series of approximations. First of all, we assume that Earth is just a sphere. We know that's not true. No, it's a squeezed spheroid usually, or in reality. So that means So that means that gravity only acts in the radial direction on this sphere. For models with a resolution of larger than approximately 10 kilometers, you can make the hydrostatic approximation. So that means we have no prognostic vertical velocity. It's diagnosed from horizontal divergence and convergence of air. We make that approximation because your solvers get a whole lot faster if you can do that, if you can make that assumption. And then we make what's called the shallow atmosphere approximation. It's a series of approximations, but it's basically doesn't take into account that as you go up in the atmosphere, the grid cells are not like this, but they're actually like this, radially coming out from the sphere. Again, these assumptions are made for simplicity. If you're into doing this kind of stuff, you always have to make sure you have a physically consistent system. So your continuous equations need to conserve angular momentum and energy, mass, etc. This was derived back in the 50s and 60s by Julian Charney, mainly. So we live in exciting times because we are getting rid of these approximations one by one. So global non-hydrostatic models, getting rid of this approximation already exist. We have them in CESM already. We have work going on, getting rid of the shallow atmosphere approximation here, which is important for geospace modeling, because as you go up there, there's a bigger and bigger difference from this distance here and the distance up there. Not that many people are getting rid of this approximation. The only group that I know of that's really doing is the UK Met Office. That's, you have to make choices on your equations that you want to use. You have to make a choice of what grid you're going to use. You have to make choice of what vertical coordinate you want to use. Typically, we use terrain following coordinates because the boundary condition is much simpler when you do that. You have to choose what discretization methods, so finite volume, a Galerkin method, spectral transforms. You choose order of accuracy. You even have to choose, where do you put your variables on the grid. So here's an example of where you could put your velocity components at the edges here, mass fields at the center. You can choose all kinds of stuff, and it all has consequences of the accuracy of your method. We are working really hard at making more energy conserving systems. It's a really tough problem. In the last decade, everybody has come on board with mass conservation. All major models except ESMWF inherently conserve mass. Probably a couple of other systems too, but the die cores we had, the new die cores we have in CSM all conserve mass now. And if you're a chemist, you really want a good transport scheme that has all kinds of properties, such as not introducing spurious extrema, preserving correlations, and whatnot. So as you can probably put the dots together, this is a lot of stuff, a lot of information. If you're interested, we had a summer colloquium here a long time ago. We wrote a book based on it that goes through all the deliberations of building a global model. I don't get any money from this. I got 5 copies. But if you want some more recent information, in this room, back in June, we had what we call the Dynamical Core Intercomparison Project Summer School. And it goes through all this stuff I've been mentioning here. You can go to that website and everything. All the lectures are on YouTube as well. So if you're interested, go there. All right, how am I doing on time? Not including questions, no? Okay. Okay. As you might remember, I made a comment on the resolution of your model is not necessarily a scale that's accurately represented in the model. So yesterday I asked ChatGPT to code up a 1D advection equation, give me an animation, took 10 minutes, done. It's absolutely amazing, if the method exists. So this is what is called, if you're into numerical modeling, this is 101, the absolute first thing you're going to work on. So it's called a 1D advection equation. So you give it a distribution. This is the yellow line. That's a square wave. Let's assume that's a cloud. Clouds are pretty well defined. So if you look at cloud liquid, it'll be 0 over there. There's a cloud here. The cloud liquid content will be pretty close to a value. Let's just call it 1 here. And if the wind is blowing from here to there, analytical solution, this thing should just translate, nothing should happen to it. So you give this thing to a model, and I'm exaggerating here, nobody uses this method. It's called just the forward Euler, the simplest scheme on Earth, and this is what you get. So you see that the solution is damped. We no longer have a top here at 1. It's going down to 0.4. It's not even moving with the right speed. See, it starts lagging, so there are dispersion errors. And then if you have higher order schemes, the different waves will propagate with different velocities, and then you start getting all kinds of wiggles and numerical noise. So it's just a 1D illustration is that your numerical methods do have errors, not as large as these ones in our modeling systems here. Get to the next. So what you can do is, what you would do if you take classes on this and at universities is you would do what's called a von Neumann analysis. You linearize your system, and then you can analytically derive what your numerical errors are. We can't do that in a full model. So a way to look at this in a full model is to do what's called a kinetic energy spectrum. So we have the wave number down here, so think of this as the length scale. And here you have the logarithmic of the energy density. So usually we look at 200 hectopascal kinetic energy. And from observations, we know that this should have a certain slope to it, a -3 slope at larger scales. But what usually happens in a model is it will start tailing off like this. We don't have as much energy at these smaller scales as we should, as observation shows us. If you don't have numerical filters in your model controlling what's going on at the grid scale, this thing here can curve up. And that's really bad, because now you're kind of emphasizing the errors in the model at the grid scale. Here's an example of what it looks like in CAM with various resolutions. So I think this is 1.5 degrees all the way down to 25 kilometers. So you see we follow this theoretical curve well, and then we start falling off. So we can see that in practice in our system. Where this line starts to fall off, we like to call the effective resolution of the model. And that typically happens at 4 to 10 delta x. So if you're doing extreme precipitation analysis at the grid scale, just be aware that I can do twist a little knob in the model, and I can change that just by numerical filters. Alrighty, we have a lot of dicores in CESM. It's a very fast evolving field, or at least it was for the last 10, 20 years. So we have a lot of new fancy ones. We have one here we just got rid of. It's a spectral transform model. It's quite similar to the dynamical core used at ECNWF. Then we have the finite volume workhorse here. It's been used for over 20 years for CAM4, CAM5, CAM6, all use finite volume. It's a good dicore, it's very fast. GFDL, NOAA went away, developed a cube sphere version of this guy, so we call that FE3. We have that in CESM. Then we have spectral element C-SLAM. That's what we're going to use for CSM3 for the 1 degree resolution. So I don't have slides on the details of that, but it's basically a local Galerking method, if you've ever heard of that. So it's kind of a high order local method. Then we have DOE's non-hydrostatic version of the spectral element dicore. We're importing that into CESM. So it comes with a lot of bells and whistles. It's C++, COCOs, GPUs, and so on. And then we have the model for prediction across scales. I showed you the OLR from that in the animation. So that's developed in the quote-unquote weather lab here at NCAR. And that's also available in CESM or in CAM. But only some of these are non-hydrostatic. So if you want to go really high resolution, you should not be using this guy or this guy. All these other ones here have non-hydrostatic options in them. We also have the capability with MPAS and spectral element to do what's called mesh refinement, and it's becoming very, very popular. Here are a couple of grids that we have released with the model in the past. We have this grid here that refines down to, I think it's 12 kilometers over Greenland, 1 degree elsewhere. when we use that, our surface mass balance of the Greenland ice sheet it looks much, much better than our default model. So the whole purpose of mesh refinement here is that you can resolve more scales in some region of interest. We have the very famous CONUS grid, if you want to look at stuff going on over the continental US. Here's an example of what MPAS mesh refinement looks like. We have a grid over Antarctica, et cetera, et cetera, et cetera. So Adam Harrington's going to talk more about that on Friday. Last but not least, I've spent a lot of time showing you horizontal stuff. But remember, there's also the vertical direction. So for a long, long time, we developed our model with a top at about 42 kilometers. So that means if you're interested in stratospheric dynamics, you should not use this model because the stratosphere is not well resolved. So we got a lot of complaints for that for a long time. So we finally changed that. So now we have a model top at about 80 kilometers. So that has a fully resolved stratosphere, and that's going to be our workhorse for CESM3, so the next version of the model. Then we also have a modeling system called WACOM. It goes up to about 140 kilometers. And then we have WACOM-X that goes all the way to 600 kilometers. So that's the geospace version of our model. When your model top is that high, there's a lot of new processes you need to include in your system. So in particular, molecular viscosity and thermal conductivity becomes significant up there. So that's part of that model as well. And that needs to be implemented in the die-core because that's a fully 3D process. Another thing I want you to be aware of, I told you be careful with the grid scale. Things are not super accurate. Also be careful with like the top 3, 4, 5, depending on where your top is, layers, because we have a sponge there to absorb vertically propagating waves that don't get reflected at the model top and create all kinds of damage. So there are heavy, heavy numerical filtering in those layers. So don't look at the solution up there. Or don't do science up there. Okay. If you're interested, here's just in words, some of the characteristics of these non-hydrostatic dynamical cores. But in interest of time, I won't go through that, but I'll happily take some questions.
At what range of model tops would you start seeing differences, or would you stop seeing differences maybe at the surface, in ocean salinity or ocean variables? What does it make that much of a difference when you start going up in those increments?
That's a really, really good question, and I don't have the full answer. But there are studies. We know that downward propagating waves that start all the way up in the stratosphere. So we typically see a change in the surface pressure field when you have a higher top. And in fact, we're just about to run those comparisons with a fully coupled system. So I would say there's definitely an impact with the stratosphere. With going even higher up, I'm not sure. In fact, those higher top models basically treat the low top model as a boundary condition. So what they want to do in the future is just prescribe the atmospheric state at, say, 40 kilometers, because they don't care what's going on below.
So with that,
they're the other way around.
So with that, you could lose some things going on.
Yeah.
Okay. Thank you.
With fast waves defining the longest time step the model is stable in, how does that impact paleoclimate runs of CAM or long-term model runs, especially considering that if there is a ceiling to how long your time step can be?
Mm-hmm. So paleoclimate is computationally a really tough problem because you have to run really fast, but your problem size is not huge. as opposed to weather forecasting where you run at really high resolution, no computer is big enough to really scale everything out. For the paleoclimate, like we typically make the hydrostatic assumption, we're not high enough resolution to be non-hydrostatic, so we don't have to deal with acoustic waves. That makes it faster. But what we have found is that what is the biggest limiting factor is actually trace advection. Typically, we have 30, 40 trace species. If you let the chemists go crazy, there would be like 250. So the cost of the dicore is almost entirely in trace advection. So, and the trace advection time step is limited by the fastest winds in your system. So for those applications, a fast tracer transport scheme is really important. That was a question.
So my question is about the mass and energy conservation. Did you imply a specific equation in your system, your dynamic course in, for example, you keep the sea level pressure to a constant for over your integration, or use this kind of conservation to verify a model, like you verify a model sea level pressure for a long time to say if it have changed, or you use this equation to keep the system stable?
Yeah, that's a good point. So I think you're mostly referring to mass conservation. And so what people figured out in modeling in the past when they didn't have inherent mass conservation was that you would lose, the worst case scenario, you would lose a couple of pascals in a 10-day run. They quickly realized this when you run a longer run, the mass of the atmosphere will start disappearing, so that's really bad. So what a lot of modeling systems now have done is either they add a fixer, so every day or so you put mass back in that was lost. That's always ad hoc because you don't know where you lost it, so you just put it in everywhere. So that's what SNWF is doing. Or you have an inherently conservative method, and then you don't need to worry about it. So if you look at moist pressure, that varies with the seasons. But if you look at dry pressure in the atmosphere, we don't have any sources of sinks in our models for that, so that is constant throughout the integration. So you can verify those things with the model. Energy conservation is much harder. No model on Earth has a closed energy budgets. So we close them artificially to make sure energy is conserved. And a couple of years ago, we published like a 90-page long paper discussing this stuff. It's really complicated stuff because energy holds everything. It's like wind components, temperature, water, everything is in there. So it's a very complicated quantity. That's where we have a lot of work to do. And whereas I would say mass conservation is a solved problem.
I have a question about the effective resolution that you spoke about. So if you have a 1 degree nominal resolution of the grid, but the effective resolution turns out to be 4 to 7 times of that. And as an example, if you think about precipitation, does that mean that anything that's happening in less than like 4 degree is unreliable? How do we understand then what's really happening with that field?
Yeah, it's a tough question. So I did exaggerate here, so just imprint it in your brains. Be careful. But there are things that are forced. So like we know where topography is. It's there. We know exactly where it is, and if that forces a certain motion, you will have stuff happening that's probably quite reliable if it's forced by the surface and so on. And the way we do apply models is we do go all the way to the grid scale in our analysis. But if you approach it from like a numerical methods point of view, we would say that there are errors at these smaller scales. But it doesn't mean they're all wrong. No, the 2 delta x wave might be correct, but it's just damped. So you might still get part of the right solution. So all I'm saying is just be careful at the grid scale. Just a
Follow-up questions, like I heard about CSM, like high-res. I was thinking how those models figure out this. It's like incorporating the topography for like having like higher resolution, or how is that?
Yeah, so the way we typically do is if we increase the resolution of the model, we also increase the resolution of the topography. So when you go from 1 degree to 1/4 degree, all of a sudden the Andes are like 1,000 meters higher or something like that. So in that way, like, you get better flow, better resolve flow around topography, and you see things are more accurate. So we see quite big benefits for going to 1/4 degree. And then we have some persistent long-term biases that don't do it particularly better. So the ITZZ, so the tropical Pacific precipitation does not necessarily look better.
So it's like more than this, like we have to add like besides topography, is any other stuff like for parameterization or other things?
Yeah, there's always tuning.
Okay.
That's really hard at high resolution, the way we tune models right now, because we run long simulations, look at top of atmosphere, radiation balance and stuff like that. And there's always tunable knobs, and they are depending on horizontal and vertical resolution. And then there's stuff that just adapts by itself. So the dicor, the dissipation, so we've implemented it in a way that it just adapts by itself, or graphic gravity waves adapt by themselves because topography file will have the right scales in it and so on. But it's a good point. Never expect a model to work well when you change horizontal or vertical resolution out of the box. There's always work to do to tune it. Thanks for bringing that up.
You first? Yeah, I have a questions about the coarse resolution and the grid size as well. When you have the square, like 1/4 by 1/4 of the degree, and it can be like across the globe and quite easy to analyze it post-processing the data set, right? But then you have the hexagonal things, and then part of them is very coarse, and a little bit of the core is very fine resolutions. And then how to post-process, also how to like, let's say, estimate the boundary bias or something like that.
Yeah, so that's a challenge. Lat long grids, we've used them for a long time. All our post-processing just plots. It's been quite the transition to move away because people's workflow are adapting for that. But our newer diagnostic packages, you can do native grid plotting or processing. But we almost always also map to a lat long grid because it's so much easier to do latitudinal averages and so on if you want to look at zonal means. So I would say we're getting there that it's seamless to look at data on the native grid. But it's been quite the transition.
I had a question about the mesh refinement. If you were doing a simulation where you prescribed emissions and you were interested in atmospheric abundance over a certain region, would the mesh refinement be useful for that, or is it? My question is more: would the increase in resolution over that region be altered by the transport processes, or does it not matter?
Yeah, so the motivation behind the web resolution is that your dynamical core in the higher resolution area will resolve things much more accurately. So you permit much smaller scales. So if that's important for whatever you're looking into, then you should use variable resolution. But you also have to be careful if your emission data is on a much coarser grid, then the atmosphere will feel this massive plume, that might be 100 kilometers across, but your resolution is 10 kilometers or something. So, and that shows up sometimes where we, by mistake, have taken a coarse resolution data set, and all of a sudden we see these big blocks in the solution. So it really depends on the problem you're looking at, and if you need to explicitly resolve more fine-scale phenomena.
Thank you.
But the big challenge is physics, again, to have that be well-behaved across these different scales. That's a tough problem.
Thank you.
With a mesh grid and like
movement towards finer horizontal resolutions, how feasible is a similar increase in vertical resolution? And how does that like impact everything?
That's a tough question again. It was really hard for us to change. We increased the boundary layer resolution between the last model version. And the deep convection behaves differently. There's a lot of variables sent to the surface that will just take the average temperature of your lowest layer, and all of a sudden it's much smaller. So that means it responds differently to the surface. So in the lower parts of the troposphere, the parameterizations are extremely sensitive to that, and it's a lot of work to make it work well. And you introduce that problem with the variable resolution, because there's this thing called the aspect ratio between your horizontal scale and vertical, and there's a lot of theoretical papers of what that should be. And the way we run variable resolution right now, we don't change the vertical resolution, so the aspect ratio as you refine changes. So kind of the vertical resolution is always kind of a little bit overlooked thing, and a really tough thing to get at. It would be really nice to refine in the vertical as you refine the horizontal, but from an implementation point of view, it's a nightmare. Just like dynamic mesh refinement, people have tried to have some kind of parameter that will determine where you want high resolution, so it means that the grid adapts, and again, that's really hard to implement. So, good question.
What are the major change from CESM 2 to CESM 3 for the atmospheric component, and what do you expect the model could perform better in the new version?
We're not done with the latest version yet. So the biggest thing we've done is the vertical resolution extent, so moving the top up to 80 kilometers. So now we have a free evolving QBO. We didn't have that in the low top, so that's kind of a big deal in the new model version. The increased boundary layer resolution has been a little surface pressure biases have been improved somewhat, but it's not like our stratocumulus decks that require very high resolution all of a sudden look a whole lot better. We have a lot of so we changed, in the new model, we changed dynamical core, finite volumes, spectral elements. It's always tuning because the diffusive properties are different between the dicores. We haven't seen a huge improvement by switching dicores, unfortunately. But it has more functionality. You can do a variable mesh refinement. You couldn't do that with the old one. You can scale on large computers, which is important. The old one did not do that. There's been a whole bunch of changes in physics. So like the boundary layer scheme called, a shell convection scheme called club now has more prognostic moments in there. Microphysics has been upgraded, so we had a very high climate sensitivity in CAM 6, I would say unrealistic. That has really come down with the new version of microphysics. And the other bias that has really decreased is if you look at the stratospheric jets in the model, in observation, they're kind of tilted. And they weren't in our old model version, but now we've introduced a new source of gravity waves called moving mountains, and that really helps with that tilt. But in our couple system, we're struggling a lot right now with the lab C keeps freezing. The tropical convection and coupling to the ocean doesn't look as good, right? So ENSO doesn't look as good as CSM2 at this point in time. So we're working really hard on making it look equally well or better. So we're not done yet, so I don't have the full answer. So it's tough to make a good model better.
Actually, we've run out of time. You can always catch Peter in the break, or he's also doing a Meet the Scientist. So, yeah. So we'll go into another. Let's thank Peter again.
All right. So yeah, my name is Rory Kelly. I'm one of the scientific work to do, translate that into how to use the computers. I'm going to give a pretty high-level overview of just kind of the services we offer and how to take advantage of them. Nothing too technical. Feel free at any point if you have a question to chime in, or I have some time for questions at the end too. So this is the most important slide I have for the whole talk, and this is just how to get help when you have a question, right? So that link there, this is our base documentation is NCAR-HPC-docs.readthedocs.io. That link, Getting Help, will take you to the consultant who is on duty. There's always, between sort of business hours, 8 to 5, there's always a consultant that's taking tickets, taking phone calls, and is even present in the building sometimes. So that gets you to whoever's working. That's how you submit a ticket, the NCAR Research Computing link there at the bottom. And tickets are a problem, like if you have a detailed technical issue that probably is going to require some back and forth and maybe looking at code or something like that. Usually submitting a ticket's the best way to do that, so that'll take you to the ticketing system. And then the last link is password help. So that 303-497-2400 is the phone number for the help desk. And they actually have a lot more visibility into password issues and account issues than the consultants do. We can sometimes tell if there's a problem with your account on the machine, but if you actually need a password reset or something, we're powerless to do that. So that phone number is your ticket there. Okay, so the things I'm going to talk about is just basically the computers we have, how to get on them, how to quickly manage data, the software we offer, how to interact with the job scheduler, which is sort of how you run work on the computer, and a little bit about customizing your environment. This is all very introductory. We do have some pretty rich documentation on all these topics, again, which is at that link. So the main HPC machine we have here is Derecho, which we've had for a few years now. It's a Cray machine, and you can see, it's a whole alphabet soup of numbers. But it's basically lots of CPU nodes and a handful of GPU nodes. I think for this class, you guys are exclusively using CPU nodes. Most of the things in the computer are pretty commodity things these days. I mean, it's AMD processors and normal memory, pretty similar to the stuff that's in a standard laptop. The only thing that's really super about a supercomputer these days typically is the network. So that's the only special part, that thing called a Cassini slingshot network. That's kind of the magic that makes a supercomputer able to scale to really large process counts and run big programs quickly. You shouldn't really need to know anything about it. If it's working well, it's working, and when it's not working, it's typically not working at all. And so you'll submit a ticket. Okay, Casper is our cluster that we use for data analysis and visualization and running small work. And this is actually my slide from last year. And last year I would have made the joke, ha ha ha, Casper is too complicated to fit on a slide almost. It's such a crazy little machine. And this is my slide from this year. We added a bunch of new nodes to it. And it is now too complicated to fit on the slide. I tried to make a slide. It was a really big table, and the text was really small, and it was confusing, and I was pretty sure it was wrong. So if you really want to know, there's a link, and someone actually put together a really big table of all the computer types on Casper. But the good thing is you shouldn't need to know much about them. Typically, you interact with Casper by asking for some resources. It has lots of them, and so it just gives you back something that matches the resource requirement you submitted. We'll talk a little bit about that later. Okay, so to access any of the systems, first you have to have Duo set up. That's our authentication method. I know a handful of folks already emailed or Slacked that they were having some trouble with setting up the authentication. Probably, email went to a spam folder or something. So if you're having issues, come see me maybe at the break or at the beginning of a lab, and we'll try to get that sorted out right away. But once Duo is set up, it's kind of a two-stage process. One, you try to access the machine either through a terminal or maybe through Jupyter Hub or something. You enter your password that you would have set up yourself. Then you wait for it to send you a push notification on your phone, and you respond. So graphically, that should look like this. That's me in the big terminal window on the left, SSHing at the top. You can see to derecho.hpc.ucar.edu. That's kind of the main address for the machine. And then my phone should give me a little notification like that. Are you logging in? And I click the green check mark, and hopefully it says approved. So that's how that process should go. And really accessing any of our services require that to work. So again, if you're having any issues with that, try to find us early because the rest of the lab will depend on that. And then once that's working, the two main ways to access the system, these days are directly from a terminal, and if you're not familiar with terminal, through Jupyter Hub, which I'll talk about in a minute. And then the addresses of the machine from the, there's my pointer. So derecho.hpc.ucar.edu or casper.hpc.ucar.edu. And you would SSH in, you can use this -L, your username, or this SSH username @ syntax for either one. And that will put you on one of the login nodes for the relevant machine. There are 8 Derecho login nodes and 2 Casper login nodes. Again, it's not particularly important which one you get placed on. It just, when you're logging in to the generic address, it finds one that it thinks is the least busy and places you there. I'm going to talk a little bit about how to view graphics from the system. That seems to be a thing that's a stumbling block a lot, is people just wanting to look at plots quickly. So there's a few different ways to do that. And this is one case where it may matter to request like a specific login node. And that's because one way of forwarding graphics back is this technology from the I don't know how I did that. Does anyone know how to make my screen big again back there? There we are. All right. But now we're a little bit. Here we go. Okay, so this technology from the 1970s called X forwarding is the oldest and least reliable and slowest way you can look at a picture from the computer, but it's still a thing that you might need to know about at some point. And for that use case in particular, X forwarding often breaks if you say derecho.hpc.ucar.edu. So I usually include a specific login node. So you can see in this command here, I said derecho1. And for whatever reason, if you use a derecho, well, that number can be 1, 2, 3, 4, 5, 6, 7, 8. Use a specific number, X forwarding usually works better. Again, it's pretty slow, but the thing you need to add to an SSH command to enable X forwarding is this -XY. And then you also, on your local terminal, your laptop or your desktop, whatever you're using, you need to have X windows set up. And that's not something we can really help with. That has to be done by you or by an administrator that has administrative access to your machine. It's pretty simple, though. Like on a Mac, you install a thing called Xquartz, and it just basically works, except for when it doesn't, which is a lot of the time. So because X is bad, we recommend some other ways that are much faster. One is VNC. And to use VNC, again, you have to have a local client installed. We recommend this thing called Turbo VNC. Tiger VNC is another one that's popular. There's a whole bunch. Any of them really should work, but these ones are free. And you would SSH onto the machine like I showed originally. We have this little script called VNC MGR. You would say VNC MGR create, then -A in your project code. Then it's going to ask you a bunch of questions and walk you through some steps, but it's all sort of things you will be copying and pasting into the terminal, so you don't need any knowledge, you just follow the instructions. And then that will pop up a little graphical login session to the machine, and that's quite quick. It's orders of magnitude faster than X Windows. Another way to do that is through this thing called FastX. This can be web-based, so if you don't have administrative access to your machine, you can use FastX to do this. If you have, if you're staff or you're working with someone here and you have access to the NCAR VPN, then it's very simple. You just go to fastx.ucar.edu 3300, and you can log in via a browser. But if you don't have VPN access, there are still some instructions to do it. Again, basically tunneling through SSH. Don't worry about that too much because hopefully you won't need to do this, but it's in the slides. You can follow those procedures or it's in the documentation. And again, that's just a much, much faster way to interact graphically with the system. And then also, Derecho and Casper are both accessible via our Jupyter Hub instance. And this is probably the way I would recommend. Like if you just need to look at a plot or an image quickly, Jupyter Hub is a pretty easy way to do that these days. And you're going to be using Jupyter Hub on Thursday, I believe, for a lab session anyway. So Jupyter Hub, you go to jupyterhub.hpc.ucar.edu, you log in. Again, it's standard Duo authentication, so your password and is your Duo password, and it will send you a push. And then Jupyter Hub will ask you, to select a server. There will be a default one for you. That will be fine. It will ask you to fill out some of this information. I think you probably don't need to change any of this. You probably, I assume, have specific instructions in the Thursday lab if there's anything special you need. But usually the defaults are fine just to get you a session. And when Jupyter opens up, it gives you a screen like this that can run lots of different standard analysis packages, things like MATLAB or Python, and you can run notebooks or terminal sessions, et cetera. And it's very clicky. And one of the other things you can do is, if you see a file name, like if you, sorry about that. So like in this previous one, this is all the things in your folder. If you just click on an image, it will show it to you. So that's also, if you just need to look at a plot or something, Jupyter Hub's a nice way to do that. One note about the login nodes, like when you SSH in, or if you're using a login node through a Jupyter session, is just remember they're shared resources. So other users are using them, and if you start running like a really, start running a CESM model on there, it'll be pretty disruptive to the other users on those login nodes. And actually, we have some software that will automatically sort of limit the amount of CPU time you're allowed to use. And things from your point of view will start feeling really slow and junky. And you'll get an email that sounds really scary telling you please not to do whatever you're doing. It's not really a problem. Whenever you get that email, it's usually because you did something by mistake. We're not actually mad at you. But it's, just remember other people are using those machines. So if you want to run like a big analysis or run a model run, do it through a batch node, which we'll talk about momentarily. But before, I want to talk a little bit about the data spaces that are available to you. So we have mainly 3 that you need to worry about, home, work, and scratch. And the things that are important are the size, how much data you can put there, and then do we back them up, or do we automatically delete things for you? And so home, 50 gigabytes, which is not a very big space these days, right? So you can't keep a lot of data in your home directory, like model output and stuff. It won't fit. It'll fill up very quickly. So that's for important code, important scripts, things you don't want to lose, because we do back that space up. So if you delete something from home, it's backed up on the cadence of hours within the current day and on the cadence of every day over the previous months and weeks. So there's always a fairly recent backup of the stuff you have at home. But again, that should be code, scripts, things you really don't want to lose. If you're working on a paper and you have a document file or something, that's a good place to keep that because it's backed up. Now, work is a much larger space. It's 2 terabytes, so you can fit a significant amount of compiled code and some data in work. We don't back it up. It's kind of too large to back up. So don't put really important things that you can't stand to lose there. Or if you're putting things in work, make sure you have a backup of it somewhere, code that's in Git or something like that. But we also don't delete stuff in work for you. It's up to you to manage that space effectively. Then Scratch is quite large, 30 terabytes, and frequently people will actually need a little bit more, and Scratch is kind of a fungible space, so if you're working on a project and you need actually 100 terabytes instead of 30, we can do that for a limited amount of time and then revert you back to a smaller quota. So the really important thing to know about Scratch is we delete things out of there. Because it's this space, we have to constantly delete things out of so we can give people bigger allocations. So never ever put anything important in Scratch that isn't backed up, because not only is it not backed up, but we actively go through and delete things, whether you want us to delete them or not. So, and then there's another space called campaign that if you're working with someone, if you're working on a project here, you might have some campaign space, but that's allocation sort of by request when you're doing a new project. So to get data on and off the system, you can use SCP or FTP for like really small files. But if you're transferring like large data sets or huge amounts of data, we recommend using Globus. And Globus is, again, something your institution, like your home institution, probably has Globus set up. So transferring from NCAR to your home institution over Globus is typically quite fast. And you can also set up what we call Globus Connect Personal on a laptop. So you can use Globus to transfer back and forth to a laptop as well. Again, we have good documentation on this, so I won't walk through it too much, but that's kind of the recommended way to quickly transfer between the systems. Once you're on the system, we manage all the software on there with a thing called modules. And you may have used modules in another system. It's a pretty standard thing. Probably the most important thing to know is just that the software we maintain on both systems is a little bit different on Derecho and Casper, just because the hardware and everything is quite different. So they can't be identical. We try to keep them really close, but there are just instances where some software won't work on both systems. So using modules or interacting with them, there's a pretty small set of commands you need to know to use modules. The way they work and what they do is, there's a whole bunch of software on the systems, and it's not all compatible with each other. So if you're using the software through modules, it's making sure that whatever's in your environment is all kind of mutually compatible. And there's kind of tiers of compatibility, and like tier 0 is what compiler are you using. And so once you select a compiler, like if I selected the Intel compiler here, then it says, okay, well, these are the things that are compatible with the first selection. And if I, for instance, selected an MPI library here, it would say, okay, well then here are, for instance, the parallel netcdf libraries that are compatible with your first two choices. So it's just keeping that stack of software sort of mutually consistent. So to load software, you say module load, the name of the software. To unload it, module unload, the name of the software. To show the things that you could load is module avail. That will show you everything that you could load. It won't, though, importantly, show you everything on the system. It'll just show you the things that are compatible with what is already loaded, right? So module list will show you what you have loaded, and module purge will remove everything and give you a bare environment. And there are a couple things. Oh, I did that again. Smart man in the back. I don't know what I'm touching, but you can make me large again, that'd be great. Thank you. Okay, so there are a couple of things. There are a couple of things that are sticky, so you might want to do module -- force purge if you really want to wipe everything out. And I often, like, in the context of a batch script, we often recommend that to make sure you understand what the environment is that you're running a job in, and it's always consistent, you do a module force purge, and then you explicitly load the modules that you want to use, and that way you're not getting slightly different versions of things run to run. If you want to save like a customized set of software, module save will save whatever you have loaded. And yeah, so probably the important thing to know there is just like there's a way to save software, and the way to save like a software environment is not to put it in a startup file, because that can cause problems. The categories of stuff we offer are basically compilers, MPI libraries, debuggers and performance tools, IO libraries, lots of analysis packages, and then little things that we have cobbled together ourselves that are just kind of conveniences. There's a lot there, too much to list, but you can do module avail to kind of start walking through some of the available software. Most things, because we install things by request, and we've been doing this for decades, almost everything you want is there. Things that tend to not be there are like customized packages for Python, and you can actually manage those environments yourself through Conda, which I don't really talk about here, but typically those are managed by users. Okay, quickly, just how to use batch jobs. You don't really need to know much about this for the tutorial this week, because the CESM scripts do a lot of this for you. They create a batch script for you, and they submit the batch script for you, and they monitor its progress and submit an analysis script for you and all that. But under the covers, there is something happening. So the batch system basically is this flow where you've logged in from your workstation to a login node, but now you want to run on one of these big compute nodes. You do that via a command called qsub, which is submitting a script. You're basically in that script, you're saying, I want this amount of hardware to run my job, and I want to request a certain amount of memory, a certain amount of CPU cores. It's going to take a certain amount of time to run my job. That's kind of the information. This is the account I want you to charge it to. You give that information to the batch scheduler, and then it schedules your job to be run. To interact with jobs, again, there's a lot more documentation on the details, but the short set of commands are usually qsub, then the name of a script to submit a script, qstat, and then the ID of a job to see if your job is running or if it's still waiting. You'll probably be using qstat during the workshop. qdel, if you accidentally, like you submitted something, but there's a mistake in there, you want to delete it before it starts to run, qdel, and then a job ID will kill a job. If you want to interactively get access to a compute node, there's this command called qinteractive, and that will basically just start a job for you, but drop you into a shell on a compute node so you can interact with a compute node. And then another one that I think you probably do use this in the workshop, I would imagine, is qcmd or qcommand. And that's basically, like I was saying, don't run heavyweight things on the login nodes. But if there was a command like compiling the model, for instance, that would be too busy to do on a login node, you can do qcmd and then -a your project, then 2 dashes, and then whatever command you were about to run that was too busy, you can put that, and this qcommand -a will run your command on a batch node instead of on a login node. So that's the way to run expensive commands, basically. And then quickly, this is what a batch script looks like. Again, these are being created for you, so you probably won't have to edit one of these this week manually, although it's something you could do if you want to see what's happening. And these pound PBS annotations are instructions to the batch scheduler. So it's just saying simple things like, that's what I want the name of my job to be. This is the account I want it charged to. This is how I want you to deal with output. You don't need to worry about that too much. -Q is almost always main, except in this tutorial, actually the name of the queue is tutorial you'll be using. That's a special thing for this week. But outside the tutorial, you would almost always use main. This is the amount of time you think your job will take. Here, that was a bad choice for a slide. That's 5 minutes. Your job probably won't take 5 minutes. We'd see a lot of mistakes where people actually think that was 5 hours. And then their job dies and they think, well, what happened to my job? And it's actually annoyingly makes you say the amount of hours, amount of minutes, and amount of seconds you think the job will take. I've never seen the seconds field be anything other than 0. I don't know why that's an option. And then this last one is like the resources you're selecting. So here I'm selecting 8 nodes, and I want each node to have 128 CPUs and 128 MPI processes. Again, you don't really need to know the details. This is all happening for you because of the CESM scripts. If something breaks, that might be interesting to look at what's actually occurring in the script. Oh, and then again, just like I mentioned, in practice, I do tend to explicitly put in my scripts what versions of things are being run. And again, that makes it consistent and also self-documenting in the future if you wonder, well, what exactly did I run this job with? And that kind of make sure it's documented somewhere. Yeah, kind of covered that already. So again, my most important slide, my first slide and my last slide, just let me know if you have any questions. Grab me at any point during the tutorials, the labs, the breaks, whatever, if you have a question. And if I'm not around, use one of those 3 ways to get a hold of someone else on the team, and they'll help you out. So that's it.
Questions for Rory? Yeah, Rory will be around at the lab session this morning, so he can help you set up your account and everything. Yeah, so don't worry if you don't get the HPC version now.
Not a question, but a suggestion is that could you send some email to us when you want to delete something on the scratch?
Yeah, no.
Because the last time when I want to look some big file on my Scratch, I find it's already have been deleted by the Scratch system, and there's no notification for me before it being deleted. So
there's not Scratch. I mean, you can imagine it's this really large, tens of petabytes file system with, I don't actually know, but certainly more than billions, probably. Trillions.
So I want to know is that there's some specific timing.
There's a time link, so it's at least 3 months. Nothing will be deleted in less than 3 months.
So
and it's not 3 months from the creation time, it's from access time. So like if you made a file and then 2 months later you looked at the file, that would reset the time. So 2 months after you looked at it, it would still be there, but 3 months after you looked at it, it might be gone.
Okay.
So yeah, so the minimum of 90 days after you've accessed it. Okay. And actually right now, so then again, that time period floats. So like if the file system is really, really full, so basically if the file system gets all the way full, the reason we delete things, the computer crashes and no one can do anything if the file system gets full. So we have to make sure it's always got space on it, right? But if we have a lot of space, then we extend that 90-day window. It's like right now, currently I think it's actually 180 days, so almost half a year that things will last. And we squeeze that window down, but it'll never be squeezed for less than 90 days.
More questions?
Yeah.
Okay, great. Okay, next we will have Kate, who will talk about the introduction to today's lab session.
Okay, now I have a green light. We're good? Okay, awesome. Okay, Hi everybody, my name is Kate. I am an associate scientist here at NCAR. I work with the atmosphere and the ice sheet models. So I use a lot of CESM, and if you guys have questions, I'll be around a lot this week, and I'm happy to help answer questions and talk to people. Some of you have already seen me on chat a little bit, so yeah, I'm absolutely here to help make this week as awesome as possible for you all. In about 15 minutes, we're all going to head into the first lab session. And so you're going to get a chance to sit down, log into the supercomputer, build and run your first CESM case. So what I'm going to outline here is just basics of what we're going to try to accomplish today. You're always welcome to work ahead. I think some of you have already done some of this. If you want to work ahead, you can. If you're a little behind, that's totally fine. We've got a lot of free time this week for people to work at their own speeds and ask lots of questions. That worked, cool. Okay, so the lab 1 goals today, the first one is to finish your prerequisites if you haven't yet. So that's finish logging into the supercomputer, finish looking around, learn about how you can access all of those software stacks, modules, workspaces, all the things that Rory was just talking about. The second goal is to check out CESM from GitHub and learn how to save the code to check out the right tag. And then the last goal is to create and run an experiment, which we call a case. So I'm going to explain that a little bit more here. Rory just kind of went over all of the prerequisites, but just for some practicalities here, we have wireless access from the UCAR visitor. If this isn't working, let somebody know. And then you need to be able to follow the one-time instructions in setup part of the material, so there's a link there that will set up your environment to use the correct queue and charge account. So every time you use the supercomputing nodes, then you have to actually tell them who to charge that, actually money. So that's important that you use the right code for that here. And then we're also going to make sure that you guys can download and install a Unix terminal, whatever machine that you brought with you. And then there's the little thing on logging into the Ratio supercomputer. I use just Y, but you can use XY or -L. Rory covered a lot of that. But again, if you have any questions, just talk to one of us and we can make sure that everything's working for you. And then we're going to get to downloading CESM. So CESM is fully open source software that we can share with everybody. You can access it freely no matter where you are. We use GitHub and Git to manage our code. So you're going to the instructions for downloading and checking out the correct tag are in that first exercise. And then once you download it, you're going to use manage externals because this is CESM2 to pull code in from many other repositories. So CESM has models from all different parts, like Peter's probably talked about this morning. And so that manage externals brings in the code from all the different repositories and sets it up for you and makes it ready for your experiment. So this is what the CESM GitHub looks like here, ESComp CESM. And you can go there and probably take a look at it today. It has issues, discussions. It's a place to start if you have modifications that you want for the model. It's a good thing to take a look at while you're doing all this so you can understand kind of how the model is set up and how everything is kind of overall organized there. And then I probably should have put this slide a little bit earlier, but I wanted to give a basic idea of how these exercises are going to work for the labs. So this is the tutorial documentation, and this is really amazing. Everybody who worked on this and put it together for the tutorial committee, it is a very thorough description of how to do all of the science with CESM that we typically do. And you can see for today, I'm going to really try to use this. Nope, that's the button you're not supposed to hit, Rory. Thank you. Okay, so which one is the pointer? Is it this one? I'm afraid now.
Top one.
Top one? Oh, there it is. Okay. So yeah, this is the documentation up here. There's the URL. You can see over here we have welcome. There's your prerequisites you've already done. We're going to do basics today. And then down here you have an exercise, your first CESM run. Boy, that's not lining up quite right. I wonder. Nope. So yeah, your first CESM run. And here it gives you an overview of the exercise. So we're going to run a basic out of the box CESM experiment. It's a B1850 case. And then we're going to check the status of the run after submitting. That's it. So you can try to do it without any hints at this point. Be like, I know how CESM works. I'm going to just try it and see how it goes. Or you can click on the yellow box, which will give you more detailed instructions, but not a line-by-line instructions. So if you want some hints and some ideas of what to do, but you still want to try to figure it out yourself, you go for the yellow box. If you just want like someone to tell you what to type, that's in the green box. So it's totally fine, especially on your first day. Click for yellow, see what we might suggest high level, and then go straight for the green to see what you actually need to type. And then underneath, you can ask some of these questions of yourself, like, did the runs complete successfully? How would you know? What sorts of files did you get? How long was the simulation? Just to make sure that you understand what you did at that point after you're finished. So this experiment today on CSM, we'd like to call our experiment cases. So each experiment is organized into one directory called a case directory. And you're going to hear that a lot because inside of that directory is all of the documentation that you need to describe everything that happened in your experiment. It describes the software stack that was running. It describes all of the, and if you dig into it, it describes all of the scripts that were used to run. It describes the component set, the configuration, the resolution, everything that you had set up. So any information that you needed to reproduce your experiment is going to be inside of that case directory, which means it's really important for your future work to be able to go back and reproduce that particular experiment. In order to create that case directory, we use a script called create new case. And this will be in the first exercise, so you don't have to memorize every little bit of this from the slide, but just to give you an overview, the create new case requires 3 arguments. You're going to give it a name, you're going to give it a resolution. So we use little aliases to describe the resolution, and your first case is going to be a 2-degree global resolution. And then we describe the configuration or which set of components, which we call a comp set. So CSM has several different components, and the configuration of which ones are active, stub, or data describes the comp set. And then you can optionally describe which machine you're running on. For the NCAR machines, we have some sort of behind-the-scenes stuff so that it figures out which machine it's running on automatically. But if you take this back to your home institution, you might have to specify, which super you're running it on so that it knows how to set it up. So like I said before, we're going to be doing a B1850 case. So that's an all-active. It means you have active atmosphere, ocean, land, sea ice, river, and wave components. Interestingly, it's not ice sheets, and since I work on ice sheets, I know that. And it's going to be a 2-degree finite volume grid, F19, G17. The F19 describes the atmosphere and land grids. The G17 is the ocean sea ice grids. The default configuration runs everything together, coupled for 5 days with the pre-industrial year 1850 conditions. So that's basically what you're going to try to do today. You can change the details of that using XML files, and that'll be part of our labs later in this week. And the model will build and run in your Scratch space, and the archive is archived to your archive directory, which is also in your Scratch space. So like some of you may have already learned that can be a little bit dangerous, and you need to be aware of the fact that that data, as it's being created, could possibly be purged sometime in the next 3 to 6 months. So just, you can move it around, you can back it up, you can do whatever you need to for that important stuff. I wanted to cover these sort of important directories that we use as part of this because CSM, every single model, it seems like, has a sort of different workflow, and this is important for the CSM workflow. So you're going to check out your source code into one directory, and that'll be the source code that interacts with Git, and we keep that in sort of its own place. I like to call it a sandbox. Some people call it their code directory. And then when you create your new case, it's going to have its own case directory, which we usually put into its own space. So in this case, you would put it in home, so it's backed up, username, cases, and then give it the case name. So you'll probably have a directory full of experiments or cases that's in a separate place from where you keep your code. And then inside of each case, you can execute the scripts to build and run the model. And then the data and the actual built files will go into Scratch. So that's your build run directory, glade duratio Scratch, username, and then the case name. And then finally, once the data is archived, it usually goes to this path that's specified in ds_root. That's an old variable, but it's been around for a long time. And so that's usually Scratch, username, archive, and then the case name there. All right, let's do this. So that's about what I've got for this overview. If you have more information, another place you could look is in the CESM forums. This actually might be a pretty old screenshot now that I'm looking at it. But this URL is still good. And I recommend that everybody register and subscribe to the forums of interest, because this is sort of a place where we crowdsource information about CESM. And you can see other people who've had probably the same problems that you have gone on here, and then other people can answer your questions. So it's not just those of us at NCAR who are struggling to answer everybody's questions. There's everybody helping each other as part of the community here on the board. Okay, and then again, here's the links and everything to the tutorial documentation, which, like I said, is very in-depth and very good. It's a great place to read, to understand everything that we have here as part of the model and how to use it and set it up and change it. And you'll be very intimately familiar with this by the end of the week. So that's all I've got. I don't know, Hui, if you want to come up and send people off. Cool.
So thanks, Kate.
Cool, thanks, Ray. Yeah. So just a quick show of hands. Who here thinks that you're pretty comfortable with what a parameterization is? Ooh, look at that. Okay, I like the confidence. It's totally not misplaced. Don't worry about it. By the end of this talk, our goal is that you have an understanding of what a model parameterization is and why it's necessary. Now, you might already have that. We're just going to try and formalize it a little bit. Hopefully, you'll come away with some familiarity with some of the main parameterizations that are present in the Community Atmospheric Model version 6, CAM 6, and the ability to find more information about any parameterization on your own. There are a ton of parameterizations out there. If you have any experience with this, you'll know that. So really, we just want to give you the tools to find out more. So hopefully, you'll get that by the end. So what is a parameterization? I like to start with the most technical definition. This is from the American Meteorological Society, or AMS. They have a really nice glossary. So this is just a good resource to have for the future. If there's ever a term in meteorology or atmospheric science that you're not familiar with, I definitely recommend checking AMS. So the technical definition is that a parameterization is the representation in a dynamic model of physical effects in terms of admittedly oversimplified parameters, rather than realistically requiring such effects to be consequences of the dynamics of the system. I do not like that definition. It's really hard to follow. My brain is not always at that level. So I also checked Wikipedia, another great resource. So a method of replacing processes that are too small scale or too complex to be physically represented in the model by a simplified process. So what does this mean in practice? Imagine you're in Paris, but your phone broke, weirdly, and you can't zoom in on any images. Just zoom broke. So you have maps, and if you have the map on the left, you have a lot of information, right? You can see the river, you can see different districts, you have roads labeled, neighborhoods labeled, great. But if you can't zoom in anymore, that's probably not super useful to actually getting around the city. What might be more useful is this picture on the right, which has different subway lines, different landmarks you might want to go to. If you want to go to the Eiffel Tower, you know it's down here. If you look at this map, I can't really tell you where it is. So this is kind of what a parameterization does. It takes something that's really, really complex, and it simplifies it down to what's necessary in order to represent that physical system. This is exactly what I said. So the goal is to capture the impact of those smaller subgrid scale phenomena on the larger resolve scale. We can't necessarily show you every road, but what we can do is show you where important things are. What other kinds of things might actually need to be parameterized? This is a really nice figure from ECMWF and their intro to atmospheric physics and parameterizations. And it gives you an idea of the large number of things that are parameterized in an atmospheric climate model and how those interact with your surface models. So if you look, for example, here at the ocean surface, you can have wind-driven waves. Those are going to impact your fluxes of sea salt aerosols, of moisture into the air, and capturing those would require really fine scale resolution. So what we do instead is parameterize that in the model. You might also parameterize different types of convection, whether those are shallow convection or deep convection, like Ben's going to talk about later. Different microphysical processes happen in clouds, which Christina is going to talk about in a bit as well. And even over the land surface, which is where I tend to look, there's a lot of interesting things that can happen. You can imagine having fluxes over an ocean or a lake might be really different than having fluxes over an irrigated cropland or an urban area. So representing each of those things within the model is where parameterizations come in. What goes into choosing parameterizations? Overall, there's some kind of big picture things that we consider, the first of which would be the impact on the Earth system. So again, this is my land bias coming in, but think about parameterizing the shape of a leaf versus how the land is used. Those are going to have different impacts on the atmosphere. The atmosphere doesn't care if the leaf is a circle or a rectangle or some kind of raindrop shape. Mostly it cares if there are leaves, or if it's grass, or if it's bare ground. So it's kind of an order of importance thing in parameterization. You would start from the most important and work your way down. Computational expense is also key. One of the reasons we use parameterizations is that it's really expensive to represent everything explicitly that's happening in the atmosphere. So what we want to do is reduce our cost having a parameterization. If you don't reduce cost, then in some way, why bother? There's also process uncertainty. So as is typical in most scientific fields, we don't know everything. That's the exciting part. We're still learning. But that can be a problem when it comes to putting it into a computational model. Ideally, what we want to have is a system of equations that describes what's happening in the real world, but there's things we don't know. So one of the nice parts of parameterizations is you can build in that uncertainty. So you can have parameters that we would say are tunable, meaning that you can go in and change that parameter and change exactly how the parameterization works as a whole. So parameterizations are especially useful for when you're not quite sure how a system works. So hopefully you have kind of a base level knowledge now of what a parameterization is. I think everyone kind of had that coming in, which is great. So it's a way that we represent unresolved and maybe uncertain processes that happen at subgrid scale so that we can actually get their impact on the resolve scale. Often it stems from physics, so things like conservation principles, but it can also come from observationally derived constraints. So with that, I will hand it over to Ben to talk about convection.
Meg. Okay, yeah, I'm going to start with convection here. Okay, well, I guess there's a radiation slide here. That's okay. I didn't prepare for this, but yeah, CAM does use the rapid radiative transfer model for GCMs, which we call our RTMG. Yeah, the details of it are not my my forte, unfortunately, but basically, yeah, it has to supply radiative fluxes at the surface and top of the model. The overall effect of the radiative fluxes is to tell us, I mean, like the sort of biggest thing it tells us is how much energy is being sort of stored within the Earth system. So if more radiation is coming in than going out, we would expect that the system is going to start to warm over time. Yeah, this can be complex code because it has to sort of take into account all the different constituents of the atmosphere, things like water vapor and CO2, you know, greenhouse gases, of course, things like that. So yeah, this can be pretty complicated code, I think, but yeah, not exactly my area of expertise. But on to convection. So we split convection into two types, you know, in our sort of rough mental breakdown. There's deep convection and shallow convection. They're basically distinguished by how large the plumes are and how deep they go into the atmosphere. So deep convective plumes can be up to tens of kilometers across, and they can sort of be driven by instability that can go throughout the troposphere. So they can reach up to 10 or so kilometers. Shallow convective plumes are smaller. They tend to be order hundreds of meters, maybe up to a kilometer or so. And that instability that's driving those plumes tends to be confined within the planetary boundary layer. But notice that both of these, if you're running a 1-degree model, which would basically mean that you have a resolution of about 100 kilometers horizontally, both of these types of convection are not going to be resolved at the grid scale, so they both have to be parameterized. If you're running a higher resolution model, then maybe you can explicitly resolve them. But in CAM, we use two different parameterization schemes for these types of convection. For deep convection, we use one that's called Zhang-McFarlane, goes back to a 1995 paper, I think, which is linked, I think, on the next slide. And then shallow convection is actually represented in CAM by a much more general turbulence model, which actually is sort of my specialty. It's called CLUB. And sort of in the course of modeling turbulence, it also sort of picks up shallow convection kind of along the way. Yeah, the Zhang-McFarlane scheme we call ZM. That's what we use to parameterize deep convection. It's based on this 1995 paper, which is linked here, but it has been updated in our model over time. So to sort of see some of the latest documentation about it, you can see the CAM6 user guide. ZM triggers based on the amount of CAPE, convective available potential energy. So the more CAPE there is, the more the more strongly convective it's going to be. It uses a mass flux approach to calculate air motion within plumes. This basically means that it's calculating the amount of air that's moving sort of layer by layer within these plumes it's modeling. CAM has parameters that control the amount of entrainment and detrainment into these plumes and out of these plumes. And the result at the end of the day that we're interested in is how much convective heating and moistening there is at each level. So ZM will give us those tendencies. Okay, so CLUB is quite a bit more complicated than ZM. It's actually sort of a full-blown turbulence model based on the Navier-Stokes equations and conservation equations. So it represents, or tries to represent completely the boundary layer turbulence. And along the way, it will also model shallow convection, which used to be handled by a different scheme in CAM. And it can also model clouds like stratocumulus clouds as well. It does this by advancing this really complex system of coupled partial differential equations, which I'm not going to torture you with, but I'll just point out that basically CLUB prognoses 11 different moments, which means that it has 11 different prognostic equations. They're all kind of coupled together. But yeah, heat and moisture fluxes, momentum fluxes, heat and moisture variances, the covariance of heat and moisture, momentum variances, and then there's one third order moment of vertical velocity. It's kind of hard to explain briefly, but that's sort of what allows CLUB to model shallow convection, actually, is the fact that it has a third order moment as well. So again, I'm not showing you these equations, but they're big, complex equations with lots of terms in them. Some of the terms are unclosed, which means that we can't calculate them on the information that we actually have available to us in the model. So like there might be an even higher order term that we just don't have an equation for. So CLUB uses different techniques to close these terms that are not already closed. Some of them are closed using a joint probability distribution function, PDF, which is a PDF of velocity, temperature, and moisture. So you can kind of integrate over that PDF to close some of the terms that we need for these equations. And then other terms are closed using sort of standard theoretical methods that go back to the 70s and 80s. These would be more like pressure terms because pressure is not in the PDF. So we can't use the PDF to close pressure terms. But that's just sort of a basic overview of radiation and ZM and CLUB. So I think, yeah, Christina will take it from here and talk about microphysics.
Okay, thanks, Ben. All right, and so really quick, raise the hands of who cares about clouds. Ah, yay, wonderful. A lot of people didn't have their hands up, but by the end of this, I think you'll have your hand up. Okay, so clouds are really important for our radiation, yes, and also precipitation, all the things, right? And so you can imagine the amount of physics going on in a rapidly evolving cloud. And so things to keep in mind are that we're trying to represent very complex features of our Earth system. And we're doing it on a 30-minute time step, and we're also doing it on a 100-kilometer spatial scale. So you can imagine that there's a lot of things that you have to parameterize within cloud physics. So I'm just going to walk you through the number of parameterizations that we do represent in the microphysics that's called parameterization of unified microphysics across scales, or PUMAs. So we represent 4 different hydrometeor species. So we have cloud droplets, ice crystals, rain, and snow. So I have nice cartoons here, but just to note that all the hydrometeors and CAM are assumed to be spherical, including our ice phase, okay? So these are some of the assumptions we have to make the calculations faster, right? All right, so then what we have is we also have water vapor, of course, and as we simulate aerosol, which I'll talk about in a second, that's how we're able to predict the number of cloud condensation nuclei. So these are particles required for cloud droplet formation. So we represent that process. And then, of course, those cloud droplets can evaporate. And then cloud droplets can grow into larger droplets or rain sizes. So this is through collision coalescence.
You probably have learned about this in some of your cloud physics classes. We parameterize this using an auto-conversion process, which basically translates or transfers cloud droplets to rain and also accretion. And then, of course, those rain particles can also evaporate. And then these also are predicted for their sedimentation. And then in terms of the ice phase, we do predict ice nucleating particles in the model. And so there is a representation of heterogeneous ice nucleation. So that's kind of my area of expertise, where we predict specifically the amount of dust. And we also do include black carbon in this model in terms of their IMP potential and their formation of ice crystals. We can also get ice crystals through the formation of, or through homogeneous freezing. So that's at temperatures colder than -40 degrees Celsius. And then, of course, the sublimation process. And then again, we have auto-conversion and accretion of ice crystals to snow, and then sublimation. And then I also want to point out, too, that we also do represent some of the secondary ice production mechanisms. Specifically, we look at riming, Hallett-Mossett riming. So again, this may be a little bit really deep into the cloud microphysics, but this is basically another ice formation process. So we do represent that as well. Okay. And then I just wanted to point out a couple, and then we do have an option in the CAM physics to add hail or grapple. And so that's something that as you guys are learning how to modify the different options for running CAM, this is something to just keep in mind if you're interested in that. And then in terms of aerosol, again, there's a whole area of research that is dedicated to understand the composition and transport and emissions of aerosol. And we do represent that in CAM. So things like sea spray, aerosol, dust, smoke, pollution, these are all things that will contribute to those cloud condensation nuclei and ice nuclei that I mentioned. And so in CAM, we have what's called a modal scheme. So what this means is that we have 3 log normal distributions to describe the Aiken accumulation and coarse modes. So these are really tiny particles, sort of the most abundant particle size, and then really large particles. And you can see that we also have to simplify this. So we have 6 aerosol species. We have secondary organic aerosols. So that's coming from not only pollution sources, but also plants and natural sources. Whoa. Okay. And it actually is very important for like photolysis, plays a role there. So maybe that was, I don't know. Anyway, and then we have sulfate aerosols, like a very, very important species in the atmosphere, especially for cloud condensation nuclei. We do have particulate organic matter, and this is mainly emitted from biomass burning. There's other organic matter species in the atmosphere, but this one is specifically for biomass burning. And then sea salt, dust, and then black carbon, which is also from pollution sources. So these are all emitted, evected, scavenged. So if it's raining, the particles will get rained out. And then what this is also able to do is predict not only the number, but the modal diameter. So these modes are able to shift both in the right and the left, and also in their amplitude. The main thing is that the width of these distributions are the same. So again, this is an example of how we simplify a very complex piece of our Earth system. I think okay. So one of the things that we also wanted to just mention is it's absolutely impossible for us to talk about all the different parameterizations that are represented in CAM or CESM. So really, we encourage you to just go down rabbit holes, is what we call it, where you think about a process that you really care about, and then you think about how to investigate that parameterization, right? And so you can do that through a number of ways. If you want to find more information about a specific parameterization, there's, of course, the papers. But we also wanted to point out that there's a terminal command that I use a lot, and I never knew about until I was working here, called grep. Do you see this right here? grep. And I actually don't know why it's grep, but you use this, and then you can search your code for anything, okay? So if you're interested in scavenging, for example, you can grep scavenging, and you'll find your way to that parameterization, okay? So that's something that you can do on your own. If you're ever curious how something's getting calculated, really getting into that source code is a really good way of doing that, in addition to these papers. And then we wanted to also specifically highlight that club, as Ben mentioned, is a really important parameterization in CAM. And if you do want extra materials, there's a whole dedicated club tutorial that Ben put together that kind of digs a little deeper into that scheme. Okay, we went through that at lightning speed, but that's good. We can take as many questions as you guys have. And so this is the time to ask. We'll do our best. to answer whatever questions you might have. So thank you.
So my question is how do you understand which like the shape of the cliffs is important or not? Like yeah.
In terms of the parameterization.
Yeah, the simplification. So
Yeah.
should we simplify that or?
Okay.
Yeah.
Okay, so in general, when you're using a model, like no matter what model it is, it's going to be question dependent, right? So if you're interested in looking at how land use change has an impact on the future climate, you may not care so much about the specific secondary ice production mechanism, right? But if you're interested in how dust will influence the future, then dust is an ice nuclei, which would be somewhat influenced by secondary ice production, right? So depending on kind of how far down the line you're looking for a given scientific question, that's what is, I would say, the most important. But then there are other ways of basically doing what we call like physics, I was gonna say avoidance, where you kind of turn off a process and see what happens. And then also perturb parameter ensembles, where we run the model many times with different parameter settings. You can kind of see the sensitivity to a specific thing to different parameters.
Is the aerosol module being updated for CESM3? Like, is it going to be like an MAM5 or something?
Yeah, good question. So CESM3, my understanding is that we will have our new sectional model as an option in CESM3. So this is where you can define the number of bins you would like to represent the aerosol size distribution. So instead of having these log normal modes, you're able to represent individual bins. So this is a much more computationally expensive method, but it is getting closer to reality. And that is supposed to be an option in CAM, or excuse me, CAM 7, but it won't be in the default run of the model, just because it is so expensive, and so it's just not something that we're going to do for the full release. Yeah. And then I'll also say there's definitely some changes that have been made in terms of scavenging and transport and some of these little fine details of it.
So you mentioned two models, like schemes, right? The ZM scheme and club scheme. So this happens at a certain scales, right? So what happens at the interface of these scales? How do you, so is there a particular cutoff where you say, okay, this is one scheme and over that there is another scheme? Won't that, how do you manage that boundary? Will that introduce any errors at that point?
Yeah, I wish you hadn't asked that question. No, it's complicated. It is, and actually, as I was preparing for the club tutorial, I talked to several people about this because it's important and interesting. But yeah, the way that they interact is actually kind of complicated. I mean, the basic idea, I think, is that club sort of delivers moisture and heat into the atmosphere via the boundary layer, and then ZM comes along and kind of tries to stabilize the atmosphere through deep convection. I mean, that's sort of like top level, like kind of like the most basic thing that's going on. But as far as where the boundary is between the two, I mean, I don't know that you can really say that there is a clear boundary. I mean, club and ZM are always on, and they're always trying to do whatever they can in terms of stabilizing the atmosphere. So, yeah, it's not an easy question to answer, unfortunately.
So both schemes are on, and then so one scheme will take precedence when it is in a particular range, and
yeah, both schemes are always active. They're always acting on the atmosphere. Club is a boundary layer turbulence scheme, so I mean it certainly is most active near the surface, and ZM can be active all the way up to the top of the troposphere. So I mean there's that difference, but they're both kind of always active. There is interaction between them, but it's not something that you can describe in a very simple way. I mean, I'm sorry not to be able to give you a nice, clean answer to that. I don't know it myself, and I haven't talked to anybody who really seems like they do know it.
Yeah, I can also add that this is something we're working on. So it is really frustrating, right, to be like, oh, it's shallow convection, it's deep, so it's treated by two different schemes, where is the handoff? So there's some really neat development led by Adam Harrington in our group, working on something called Club MF. It's basically adding on to Club so that Club itself can do deep convection too. So that it's a unified scheme that handles shallow to deep transitions, and it can kind of capture those tails of organized deep convection better than just having two separate schemes. So it's not the default option, but I'm hoping it'll be an option in CSM3 to turn on at least and investigate, but it's not ready yet.
We had a question from there first.
I think it's a question for Christina. So you mentioned about the particulate organic matter, and you said it's specific for biomass burning aerosols. I'm just wondering, like, is there still like SOA for biomass burning aerosols, and what are the difference between like POM and SOA?
Yeah, so this is a great question. So right now, the way we represent biomass burning emissions, it includes black carbon and primary organic aerosol as a primary emission, and then also the gases. Those gases then go on to contribute to the secondary organic aerosol, right? So the particulate matter, think about, if you know, brown carbon is kind of what it's trying to represent. The other aspect of that is that the MAM4, I mentioned that there were 3 modes, but there's technically a 4th one. I just was trying to keep it simple. But basically, the 3 modes are all hygroscopic, so they will all be cloud condensation nuclei. But then this 4th one is a non-hygroscopic particulate organic and black carbon. So when things are initially emitted, they don't interact with water. And then as they age, they become more hydrophilic. Yeah. So that's I don't know if you followed that, but
No, that's a helpful system.
the aerosol people in the room know what I'm talking about, sorry.
All right, thank you.
Yeah, thanks.
This might be like a very basic question. So I was just wondering, so for example, like the parameterization examples you mentioned, so those are technically like another system that is a small system that coupled with like the big system. So I was wondering if, so what kind of system can be parameterized, and what other system like couldn't that must be coupled or can't be parameterized?
Yeah, I could try. That's a super good question. So, right, basically parameterizations are systems of like, increasingly, you go from large to small size, right? So you can have the atmosphere system as a whole, has a lot of parameterizations in it. Then we have convection that's parameterized, and then we have microphysics within the clouds that are parameterized. You can imagine, I mean, in the land model, right, you parameterize something like photosynthesis, has parameters in it that we can vary and understand better. So I'd say pretty much any physical process in reality is something that you might want to have a parameterization for. The difficulty is, can you make it computationally efficient? Can you make it somewhat realistic? Do we have observations to tell us what it should be, basically? And is it going to have an impact on the atmosphere? And so that's kind of the argument of like, do I need to parameterize the shape of a leaf, or, you know, the presence of a van versus a car, as opposed to like, oh, there's traffic and humans here impacting the system. So you kind of make this judgment call on what's going to have the biggest impact. But in theory, you could parameterize pretty much anything.
Does there have to be like a separation in scales, like a difference in scales, or?
I don't know. I don't think so.
Do you mean, sorry, can you say that again?
Like, does there have to be like a like difference in scales of those two systems to be parameterized? Yeah, I was wondering, like, for example, all of like the ocean, how the ocean affects the atmosphere, can those also be parameterized, or is it not possible?
Like a coupling between the different.
Yeah. Can like all coupled systems be parameterization?
Yeah. So the coupling is something that we absolutely parameterize in the model right now. So if you go into the coupler within CSM, you can look at how do we parameterize the fluxes from the ocean to the atmosphere. There's actually different parameterizations that you could play with. So we have 3 right now that you can turn on and off in CSM to understand what's the impact of that coupling and our parameterization of it. Yeah, so it can be on the same scale.
In high-resolution versions of CAM or CSM, do these parameterizations still hold true, or do you explicitly model more of these processes in a higher resolution version?
Oh,
you got it.
Sure, yeah. If you're running a higher resolution version of the model, you might get to a resolution where you could turn off a parameterization, for example, like ZM might be a good candidate. I mean, that, those kinds of plumes can be tens of kilometers across. So I mean, if you're running a resolution that's maybe a few kilometers, then you probably don't need to have ZM turned on at all in the model. And if you get down to running like large eddy simulations, for example, you might not even need to have club. You might be able to resolve the turbulence itself if you're running on really fine scales. But let's see. I mean, I personally have run the model at a 1/4 degree, but I mean, even then, I believe we're still running with ZM and that kind of thing. It's very expensive to run it at those really high resolutions, so that's not done as much. There are some people who are working on that. We have some simulations called diamond simulations that are just a couple of kilometers, so they're very high resolution. And I think probably ZM is probably turned off in that setting. But yeah, it's a good question.
You mentioned parameterizations for aerosols, right? How are these parameterizations actually made? Because aerosols, I think 5 aerosol species are there, 5 or 6 aerosol species are there. And aerosols can change in their characteristics over different regions. Even the same dust which is over India might not be the same dust. And that can also go through aging and lot of things. So how are these parameterizations, how do you take into account all of these difficulties or in the parameterizations into account? Do you do it over multiple regions or?
Yeah, that's a great question. So a lot of what we do are thinking about the global climate scale questions, and so being able to reproduce like past climates and things. So we want to make sure that our aerosol emissions are able to reproduce volcanoes or massive dust sources, things like this. In terms of being able to get the correct composition and chemistry right all the time, that's an active area of research. So if you're a chemist or an aerosol person, that is like a whole open place to do a lot of research. But I will say that there's a ton of development in our atmospheric chemistry observations and modeling lab, ACOM, and a whole team working on exactly this point of thinking about how do we make sure that the model is representing the chemical evolution as these particles are being transported. And then there's also specific research groups who look at things like differences in mineralogy, depending on where you are, right? But these are very kind of niche projects. And so what typically CESM is being used for in sort of the more climate application, it's kind of one of these things where it's like, okay, we can't really represent every chemical equation in the atmosphere, and so we have to make some realistic decisions about how complex we can keep it, and so then you have simplified chemistry. And so you kind of get close, but yeah, this is this whole idea of this micro scale evolution and then the macro scale climate piece is a whole area of research, as you're probably familiar. So anyway, there's a lot of development work there.
Hey, I was wondering, for convection, is there some kind of skill awareness in the model?
Skill awareness.
Yeah, that you're like if you're going to high resolution, that you're not kind of double counting for convection.
I don't know that there's an explicit skill awareness in club or in ZM. ZM is a little bit more fuzzy to me. We might want to double check on that, but club, I'm almost certain it doesn't really have an explicit skill awareness as far as the horizontal resolution is concerned. But as far as ZM, I don't think so, but I can't 100% guarantee that.
Yeah, I'm pretty sure it doesn't.
So, like, I think in the previous presentation you showed that, like, for this 3 or 5 kilometer resolution, you showed like 2 maps of the clouds patterns for high resolution, with and without the convection turned on. And even without convection turned on, you do have deep convection. So, like, how does it then basically not double counted, or like, I maybe don't understand how it works.
What was this? I'm sorry, I'm not sure if I understood the second question. What was it?
You're talking about MPAS. You have MPAS at 3 kilometers that resolves it, and then you have the parameterization. Does MPAS also double count? Is that what you're asking?
Yeah, exactly.
MPAS is good.
Because when you're at the border between permitting and parameterization, are you double counting? Because some of the grid is able to resolve the physics. Some is being parameterized.
I want to say it's a possibility, but I will also say that none of the three of us work on MPAS. So
Totally different model.
we don't really know.
Totally different model.
Yeah, that's the hard part is, so right now in the atmospheric model, there's a community atmospheric model, CAM 6 developing CAM 7, and then there's the MPAS model, and they have different parameterizations and different things they do. And so most of us are an expert in one or the other rather than trying both. Yeah, that's a good question.
So for club, so my understanding is the club is, the series are mostly built up observations from mid-latitude or tropics. And I guess my question is how confident we are for club to parameterize the boundary layers in the high latitudes.
High latitudes versus the tropics?
Yeah.
Well, club itself, the sort of Larson group that develops club at the University of Wisconsin, they do test club in a kind of single column setting with lots of different test cases. It's probably true that most of them are nearer to the tropics. I don't know offhand if there are high latitude cases, but yeah, it is a good question. As far as like how do we gain confidence that it's working well at high latitudes is what you're asking?
Yeah, because you don't have any data to validate or test it, or I would say it's a lot of, you miss a lot of data, or when you develop the theory from the very beginning, and we don't, consider or include these scenarios or boundary layer cases in the polar regions, which might be different from those you get from the mid-latitude.
Yeah, I think it's a fair point. I mean, it's probably true that we don't have as much validation for club, at higher latitudes, to my knowledge. I mean, club is tested against a number of different case studies, but it might be sort of weak as far as the testing goes for high latitudes. When we run it in CAM, of course, we are sort of comparing it to lots of just like different diagnostics, and we can sort of turn different knobs to try to improve club's performance in different regions of the globe if we think that it's not doing as well as it should be somewhere. But club is such a complicated piece of code that, if you tweak one parameter, it can really have kind of effects all over the place. So it is challenging. I mean, one of the main challenges of club is just stratocumulus versus shallow-cumulus. So even in the tropics, we struggle to get that balance right. That's like a long-standing problem. So, as far as my work with club, that's kind of the thing that I might, focus on or look at most often. But yeah, the high latitude versus the tropics, that's kind of like a whole other area that, we would want to get right. And it's tricky. It is tough to kind of get the whole globe right. Yeah.
Yeah, I guess I wanted to just make one comment on that too, which is just as you're using the model for whatever application it is, and we've talked about this for the high latitude clouds, but it really is important just to understand what permutations are active and that you would make sense from your physical understanding of what it is that you're looking at to care about. So like if you're looking at Arctic clouds, then you probably want to see what your boundary layer is doing, right? And then I just wanted to say that it is very complicated. We kind of keep saying that, but just to point out that, global modeling has come a long way. We've added a ton of sophistication to what all we're able to represent, and all of these interactions, like for example with sea ice or something in the polar regions, those are all just like very full areas of research. And so as we've added more complexity, you kind of add more uncertainty in a sense, but then you also add more things that you can explore. And so that's what makes CESM a really fun model to work with for research. But I just want to kind of comment that I feel a little bad that we don't know all the answers to your questions, and then I don't think it's reasonable to have anybody know all the answers, so I just wanted to point that out, so.
Yeah, I was thinking, are there any time that the parameterization is not valid anymore? Is because of non-stationarity or any vegetation changes, land use changes, or any time can happen?
Absolutely. So one of the key parameterizations, for example, controlling fluxes between the surface and the atmosphere is Molnar-Nabokov similarity theorem. This assumes that you have a homogeneous surface, so kind of a one surface type, and that the boundary layer is well mixed. Now, I think from just looking outside, that homogeneous surface assumption is quite an assumption. At maybe 100 kilometers, you can say that on average it's not too different, but when you're actually getting down to fine scale, that assumption breaks down, and so the parameterization is no longer the best choice. So that can happen in any range of circumstances, which is why, as Christina was saying, it's so important to know which parameterization is active and is it valid for the question I'm looking at and the scale that I'm looking at it and the time scale I'm looking at it. So it's kind of useful to know like all of the different things and just be aware of those situations where it can break down. Yeah, but it's totally possible.
Yes, as for plot part, and you mentioned that evolution is 10 kilometers. So I was wondering that do you focus on the microphysics of the clause, or you just focused on the parameterization based on the experience or the lab data?
Okay, just to make sure it's clear, the model is 100 kilometers, not 10 kilometers. I wish it was 10 kilometers. I think we all do. But so just to make sure that's clear, 100 kilometers. And then the parameterizations are kind of a mixed bag. There's some that are laboratory, there's some that are, so like the rhyme splintering, for example, is some lab studies that are now being challenged. And then when you look at things like auto conversion, that's from a large eddy simulation. So they run large eddy simulation, that's really high resolution cloud modeling, and then basically parameterize the data that comes from that. So there's kind of a combination of lab, and then also some observations that we can sometimes use to constrain the model, but that's less so been used in the past and is becoming increasingly so used. So anyway, so it's a combination of both laboratory, high resolution modeling and field observations.
Question?
I had a more of a practical question related to how we look at the code for these parameterizations. You mentioned, we can try and just simply investigate the source code and look at how so is it just that you go into the Fortran code essentially and see how they're hard coded and make sense of what it is? And because I was just looking at this, dozens of Fortran files for each, for size or for pop or whatever, and we just go through them, essentially. That's the rabbit hole you're talking about?
Yeah, so that's that grep method I was talking about, which will help you if you go into your source code directory, and let's say you want to look for ZM, let's say. Then if you use that grep command, you're going to be able to find at least which Fortran files have something related to the ZM scheme. And you'll start to gain some familiarity, but it's not something, I don't want you to be like, I need to be able to read thousands of lines of Fortran code. That's certainly not the expectation or a reasonable way to do it. It's just that if you're curious kind of where things are getting called and you want to look at the calculation, that is a good place to go, or a good way to do it, yeah.
Is there a way to differentiate like biogenic, anthropogenic, and biomass burning SOAs?
It is all in the same category. Okay. So the only way I can think of that you would be able to do that would be to turn off certain emissions and run the model, let's say 3 different times. Okay. And then you could be able to see the difference in the SOA, but that's even tricky for it's not super great. But there are other versions of CAM that have more sophisticated chemistry. So like the whole lab at NACOM, they have their own versions of CAM that maybe don't care so much about all the details in club, but are really detailed with the chemistry. So again, it's one of these, I don't know if you guys have talked yet about, fit for purpose of a model. And so if your research question has to do with this attribution of SOA to different areas, you would want to set up your experiments in a certain way, or maybe use a version of the model that is able to answer those questions. Yeah.
Okay, we ran out of time. Thank you, everyone.
Everybody, and today I'm going to give a lecture about Willy inside the CSM factory, how we build a model. And I have been using this model for a very long time. I did my thesis over 25 years ago with, it was not called CSM at the time, but it was a previous version. It was young and clueless. Now I guess I'm just clueless, but Then this is, I'm going to bring you this. Then what I'm going to talk about in this talk, first I'm going to give you an idea of the timeline when we build a version of the model that you are using for the lab, CSM2. Then I will talk the art of tuning, and then I will tell you some model development tale, and in particular what can go wrong when you do model development. Then basically, you saw this morning, this is CSM, then it has like a lot of components talking to each other through a coupler. And I'm going here about the timeline, how long it takes to build a model like this. Then basically for CSM2, we started to build this model in 2010. And every working group was working on the component. Then the LAN, the CIs, then everybody, and it's for about 5 years, every working group was working to improve the component. And then after these 5 years, we started to, first, what do we do during these 5 years? Then we focus on aspect that we want to improve. Then for the atmosphere, we were trying to improve dynamical core. Sorry. I don't think I'm going to use this because I'm going to, Okay, then, sorry. Then for the atmosphere, we were trying to change dynamical core resolution. Then also we play with physical parameterization. We do a lot of uncoupled simulation just with the atmosphere only, and we look at diagnostic. And the other component were doing the same thing. After 5 years, we start to put everything together, and it takes 3 more years with a lot of meeting and a lot of new simulation with over 300 configurations that we tested. And we run thousands of years and look at many diagnostic, many plot. And at the end, the model was released in 2018. Then basically, you see that from the start to the finish, it took 8 years. It's not like something that's released really often. Of course, it's not like straight. We build a component and then we couple. There is like some back and forwards. And this time, we started to do the back and forwards between working on the component and then coupling even earlier in the process. And along the way, we are doing what we call model tuning. And this is model tuning. Often people wonder what we are doing when we do the model tuning, and I want to give you an example of how we do the model tuning. Then it's what I call the art of tuning, and you will see why I call this art. Then basically tuning, you are going to adjust parameter, what we call in our jargon the tuning knobs, to achieve the best agreement with observation. Then of course, when I talk about tuning knobs, the parameter, it's parameters that are weakly constrained by observation. I'm not going to tune gravity or parameters that are really well established. But for example, a parameter that's not well established, it's what we call in the model DCS. It's a threshold diameter to convert cloud ice particle to snow. I'm going to show you what it is. Then basically you have cirrus cloud, very high in the atmosphere. They are made of ice crystal, what we call the cloud ice. They're at high elevation, higher than 5 kilometers. And basically in the model, it can look like this. You have ice crystal that are bigger, some ice crystal that are smaller. And then we can decide the big ice crystal are going to fall out of the cloud and the small crystal are going to stay in the cloud. It's what we call a conversion cloud ice to snow. And basically this threshold diameter, we are going to say all the crystals that are bigger than some threshold diameter, some diameter, are going to fall out. For example, it can be 500 micron. Then what it's going to do on climate, then here I'm going to show you an example of, on this side, on the left side, a cloud with smaller DCS, that it means there is less cloud ice because all the big crystals fell out. While the larger DCS, you have more cloud ice. And what's going to be the impact on the climate? That basically, if you have less cloud ice, the infrared radiation, you will have more infrared radiation that can go out back to the space. While in the right side, I have more cloud ice, and you will have less infrared radiation that can go back to space. Then what's going to be the impact then on my simulation? Then we do this to do the best agreement with observation. And here I have the Earth's budget. You might be familiar with this plot, but basically this is here where I'm going to adjust my DCS and I'm going to change the budget. And usually when I do this in simulation, this is just an example of a parameter that I pick because it's easy to understand. I hope it's easy to understand. But there are many other parameters. And what we try to adjust in a couple simulation, it's to have the top of atmosphere radiative balance that should be near 0. And why do we do this? Why is it important? Somebody has a clue? Yeah? Yeah, exactly. Then if you start to inject heat in your system, the atmosphere has very low heat capacity, then everything is going to be in the ocean. The ocean is going to warm, and I can guarantee that after 2 days, I have all the oceanographer in my office complaining about this. Then this is why we want to adjust the radiative imbalance. And this is one thing that we are tuning, but there are also a lot of other targets that we are tuning. Then we look at the cloud forcing, we look at the precipitation, the ENSO amplitude, the AMOC, the sea ice thickness at an extent, and we look at a lot of other things. And what you should know is that it's always impossible to have everything right. And when you do the tuning, you will have always choice and compromise. Usually when you do something better, it makes something worse. But what the good thing about this model tuning, when we are doing this tuning, we learn a lot about the model also when we are doing the tuning. And also the good news is that overall, the tuning itself has little impact on the scale of the model. Okay, then now I want to bring you, this is for the fun, then what can go wrong when you do model development? And a lot of things that go wrong. And I'm going to show you a few examples that we had over the year. Then the first example, then what I'm going to try to convince you is that when we are doing the coupling, when we are putting all the components together, we are unleashing the beast. Then when I do an emipran, it's a type of run where I prescribe the SST, the sea surface temperature. And when you prescribe the SST, you have a really well-behaved model. It's basically a EMIP simulation. I just run the atmosphere and not the other component. Then the model, the SST are prescribed, even if your top of the atmosphere imbalance is very positive, you prescribe the sea surface temperature, nothing can happen. Then your model is really well behaved. Once you put a fully active ocean under your atmosphere, you start to have couple bias and feedback, and everything can go wrong, and it's what I call unleashing the beast. And I'm going to show you a few examples here. Then my first example, it's during CSM1. Then it was an older version that you are using right now that was released in 2009. And at the time, we did a lot of the tuning in EMIP mode, then with sea surface temperature that were prescribed. And we had really a perfect simulation. I put here under some stuff when I say CAM SST, people know what I'm talking about. Then we had really a really good simulation in our atmosphere-only model. And then when we couple, then we started to see a very strong cooling, huge sea surface temperature error in the North Pacific. We had a bias that was over 5 degrees. And basically, you see here the evolution of the temperature error in this region over 12 years, and you see that this bias grow really, really quickly. And basically, what was happening, we started to have a little bit colder SST. Because we had colder SST, we had more cloud in the North Pacific. Because we had more cloud in the North Pacific, we had even colder SST. And then because of this, the sea ice started to grow. And because the CI start to grow, we had even called the SST, and in no time you had this simulation that ran away. And what one way to do with this version of the model, even that we had the perfect simulation in EMIP mode, we had really good cloud forcing, we had to make the cloud forcing not as perfect to avoid to have this feedback in the couple simulation. Then this is my first example here. My second example of unleashing the beast, it's when we try to change the dynamical core of the model. Then when we try to go from finite volume to spectral element. And I think Peter might have showed this in this talk this morning, but it's two different dynamical core and two different grids. Then when we go from there to there, in theory, nothing can really happen. And it's true that when we did the CAM standalone simulation, the finite volume and the spectral element, it was very, very similar result. It was even boring. We changed the dynamical core and it looks basically the same. And, but then when we started to couple, we put this with the ocean being under, and then the sea surface temperature stabilize SE, then it's the spectral element in red here, they stabilize half Kelvin colder than in finite volume. Then you have always a spin up at the beginning of the simulation, but it was really too big and it was a showstopper, then we could not continue the development. Then we had a big problem. Then we spent a lot of time to try to determine why we were having this. And at the end, we track, the reason was this is the zonal surface stress, and it was in the Southern Ocean, and you see that between, in black, the finite volume and the spectral element, you had this very small shift of the maximum. At the beginning, we didn't even pay attention to this because it seems really, really small. But then what was happening, why was it important? And I'm sorry, the color are different because some plots are coming from the atmosphere and the others are coming from the ocean diagnostic then, but I put each time the legend. Now finite volume is in red and spectral element is in green. But basically it's important, even this small difference, because we are in a region where you have upwelling of cold water, and then it really matters where the maximum is. And what was happening then, this error was after advected by the ocean circulation, and you had an error that grew really quickly, like in the plot that I was showing before. Then basically, it was this small change in the zonal surface stress that was located near the location of the upwelling zone, and that was carried over by the ocean circulation that was responsible of the SST cooling that I was just showing here. And then, in this case, we didn't succeed to solve this problem in time, and at the end, we released the model with the finite volume as the default die-core, even that our original plan was to use spectral element. And sometimes we don't solve our problem. The last example that I want to show you, it's during the CSM2 development, when we started to couple everything together, we had a problem with the Labrador Sea. Basically, here I'm showing you the observed sea ice extent. And if you look here, you have a very thin black line. And this is where the sea ice is stopping. And this is in CSM1, and you see that the sea ice extent is pretty close to observation, and the Labrador Sea is ice-free. Then now, this is now, the Labrador Sea now in this region, in CSM2 development, you see that the Labrador Sea is ice covered. I'm looking here at the planet from the top. Then this was, again, a showstopper for us. And then we spent tons of time, and it's why it took us, one of the main reasons, it took us 3 years to really release the model by the time we started the coupling. Yes? I'm going to show you, but we try like hundreds of.
really strong, like overly strong deep convection in the CSM.
This is, yeah, then I'm going to show, yeah, then the Labrador Sea issue is a very complicated, very close to be flipping over, and there are a lot of suspect, and it can be the runoff, it can be the precipitation, we try a lot of things, and we have problem right now in the current version of the model, but this was in CSM2. Then let me show you the plot after. Then this is why did we have a problem here, and why was it freezing? It's because in CSM1 we had a bias. We were too warm and too salty. While in CSM2, we were too cold and too fresh. And even that the bias were about the same amplitude, they were opposite sign. And in this case, the bias was helping us, while in this case, it was not helping us, it was making the Labrador Sea freezing. And the problem with the Labrador, yeah, then this is really, we got stuck the Labrador Sea for a while. And then the problem with this also is that the sea ice could build sometimes after 1 year. This is time series of the ice fraction in the Labrador Sea in different version of the model. In CSM1 and CSM 1.5, you see that it was very stable, but in CSM2, and I pick here simulations that were freezing, we had some that were not freezing, but sometimes it freezes after 1 year, sometimes it freezes after 40 years, and we had even one run that freeze after 100 years. And here in CSM3, we have one run that froze after 225 years. Then it can be really, you do a long simulation and then suddenly it freezes. And when it freezes, it never defreezes. Then we did like multiple attempts to fix the issue, and it was not working. Then it was really robust. And at the end, we had unexpected help from the estuary box model. At the same time, the oceanographer was working on the estuary box model. Don't ask me what it is exactly. Will ask an oceanographer when he will be in the room. But when they include this, suddenly you see that the bias were going to go the good direction. The surface salinity increase, and then the bias compared to the control also increased. We had a positive bias. And then it helped and it solved our Labrador Sea in CSM2. Okay, then I hope I have convinced you that coupling is unleashing the beast. I think I have 1 minute left, it's good. Then in summary, then when we build a new version of CSM, it's a very long process. Then first we build the component, and after we couple together, we do a lot of back and forwards between the two, but you see that for a version of the model, it went from 2010 to 2018, and we started to build CSM3 just in 2018, just after. We are in 2025, and you see that it's about the same time that it takes to release a new version of the model. Then I hope, I explained you what was the art of tuning, that it's adjusting parameter, what we call the tuning knob, to achieve the best agreement with observation. And again, tuning involves choice and compromise, but usually we learn a lot about the model during this exercise of tuning. And I show you 3 examples of, here I call the art of coupling, when we unleash the beast, and I show you issue in CSM1, in CSM 1.2, and in CSM2. I have tons of examples like this. Okay, then I want to thank question. I want to say that I'm the only person who do cartoon. I'm really lucky. I have my husband and my son that are doing cartoon. Nothing is ChatGPT. I come and I tell my husband, "Can you draw this?" And just like, and this is my son. It's a Minecraft. My son is your age, but he likes to play Minecraft to relax. Okay, then if you have any question, I can answer now, otherwise I'm here.
Questions for Cécile? Yeah.
So if the MIP run is perfect,
Yeah.
and then you go to coupling and things are
horrible, what does that suggest? Does that suggest that you're missing a process in the coupling and the AMIP, or maybe the AMIP wasn't so perfect and you had like biases that were like sort of competing with each other in opposite directions? What does that suggest?
Then first, when we do the couple, the AMIP, you have the correct SST. Then you force with observe SST. And then when you let the model go on its own, you will have already an SST bias that can be an issue for the simulation. And then the fact that it's perfect in the AMIP simulation, I was showing here in this, I just showed the temperature here, but what we really like in the simulation that we had over there, it was that the cloud forcing were really, really good in the North Pacific. But then, because we had SST error and, yeah, this is really this feedback. We are missing process, obviously, but it's really hard. And we have like SST error that don't exist in the image simulation. And it's the two process. Yeah.
But does this suggest maybe tuning in the ocean is important, or like we need to tune both together to be able to?
Yeah, we do a lot of tuning in the ocean. And for example, for this, what I was thinking for this one, what would have flagged the atmosphere people. I'm showing here example of the atmosphere because I'm the atmosphere liaison, but I sold the couple simulation, but it's what I know the most, but we do also tuning in the ocean. And for example, here, we could have solved the problem as atmospheric scientists by increasing the mixing in the ocean, but the oceanographer didn't really want to go there. But we do also a lot of tuning in the ocean, and you will have oceanographer later this week that can talk about this. Then right now, when we are adjusting we have again issue with the Labrador Sea, and we are doing tuning in the ocean to this. I don't know who was first.
How do you know when you're done tuning?
Then I think the perfect is the enemy of the, I don't know. And you said it's the perfect, sometimes you can spend your life to do a parameterization. At some point, right now, we have a lot of pressure, we need to release a model. Especially if we want to be part of CEMIP, we need to release. We are having a problem with the Labrador Sea right now, and there was stuff that we want to include in the ocean that we are not going to put because we have a simulation that's not freezing without this modification. Then this is...
So you basically tune until the deadline.
No, it's not, it's a little bit this, but it's not until we have to have a simulation that's stable, that basically when we are doing the simulation, we want to represent the 20th century, we want to have simulations that are realistic, but we want, if you let those, we want always to be better. We always, and people have plenty of people here are so creative, and they have always tons of ideas how to improve the model. At some point, we have to stop and to have a release of the model. And if it's good enough, one of the things is that it should be maybe better than the previous version, and then also that we have new process that are included at some point when we included CAM5, we were able to have the indirect effect, and it was something that we wanted to include in the model, but it makes stuff much harder than when we didn't have the indirect effect, the cloud indirect effect. And
back there first.
So how do you tune AMOC? Like what is the standard?
I'm not an oceanographer. I cannot answer this, but you will have ocean people. I know they look at this and they like it to some 26% value, but I'm not looking at this at all.
I think this first.
So when comparing with like other modeling groups, what is the main cause for differences in models? Because I assume like a lot of the physics stays the same. So is it mainly the parameterization schemes?
The parameterization can be different, and there is also what what people, then in some group, they want, there are stuff that are more important to get right. And for example, you have a lot of center have problem with the Labrador Sea freezing. And a lot of centers don't care about it. We really do care. Then we want to fix it and we don't want to release a version when the Labrador Sea is freezing. But you have, as a group, that would have different. And I think it's also very useful because when you start to have model intercomparison, you can look at different model. And sometimes we will import a parameterization of another model because we know that it gets a better result.
Okay.
Okay, you then,
And I'm going to be in the lab. I love students. Yeah.
So
yeah, new user.
yeah, so the tuning is based on the observation, and we don't have the observation from future.
Mm-hmm.
And like, how much do you tune to look at the current observation that not impeding the ability to predict in the future?
Then, yeah, and there is like no perfect solution. That our rationale is that if you want to be able to have at least little phase to predict the future, it's to be able to represent the present day and the 20th century and everything that we have observation. But we know that there are processes that you cannot guarantee that the parameterization that you build in a warming world are going to stay the same. Yeah, it's our best bet. And me, I'm not really looking much at the future scenario. I'm looking really more at reproducing and understanding the 20th century.
Yep, and the fact that you see the Labrador freeze in CESM and that some other modeling centers have the same problem, does that then imply that we might be just very close to a tipping point in the real world, or do you really say it has something to do with the initialization, the data that you
Each time I flew over, I look if it's frozen. Just like, yeah, no, the problem, we have only one realization of the planet Earth, then we don't know, but yeah, I think that in the model we are close to a flipping point. I don't know in reality. Until it's frozen, I think that the model are getting it wrong. But if it starts to freeze, I had like for April 4th, I did a big joke, and because the Labrador Sea was freezing, and I just did like if the New York Times had done release, the Labrador Sea is frozen. Just like it was yeah. It was my April 4th.
So if there's no deadline, like how do you like avoid model overfitting?
Sorry,
say if there's no deadline,
we have
you can do in.
We have deadline. Right now, I would like to take 1 year of vacation this summer, but I don't know if it's going to happen. We have deadline. We are right now our deadline to finish the model is September 30, and it's really. I mean, to have a frozen version of the model, we have deadline. It's not,
okay.
Yeah.
There's a deadline, but like speaking from the model itself, so how do you like avoid model overfitting? Because sometimes if you like over tuning the model to some specific parameters, that might like falsely attribute the bias to some process.
Then we don't have hundreds of parameters that we are tuning. Right now we are still tuning by hand. And basically we are doing a simulation, we are changing parameter, and we are looking at the improvement of the simulation, but we have very few parameters that we are tuning, and we're not tuning so much thing. The atmosphere, the top of the atmosphere imbalance, it's something that we are tuning. But we are not tuning so many parameters. But yeah, right now we are still tuning by hand. There are efforts to automatize it, and so far, I know it will come, but so far machine learning, there have been efforts long before machine learning, they cannot do better than a bunch of scientists sitting in a room and discussing and say, oh, this is wrong. But we have really effort to develop machine learning to help us with the tuning to try to understand what's going on. But right now, it's still a bunch of scientists sitting together that does the best tuning. I think we are out of time.
Yes,
But I will be here all week.
Okay, let's start.